everyone, welcome to this explainer. You know, we hear terms like neural networks and algorithms thrown around literally all the time, but the true foundation, the actual engine driving all these models, is deeply, deeply rooted in mathematics. Today, we're going to completely demystify the math behind the magic. We'll explore exactly how statistics informs machine learning models, taking raw, messy numbers and transforming them into systems that can actually learn and make incredibly complex decisions. Okay, let's just dive right into it.
So here is the big one. How does a machine actually know anything? Honestly, it's a question that feels a bit like science fiction, but the reality is wonderfully grounded. Hooking a computer up to a power source doesn't just instantly grant it knowledge, right? AI is absolutely not magic. It's essentially using math to solve the ultimate computing problem, uncertainty. In the real world, data is just messy. It's incomplete, it's noisy. And to make any sense of it, machine learning models rely on mathematical frameworks to find patterns and make highly educated guesses.
To really wrap our heads around how this works, we need a core mental model. Think of it like this. On one side, we have statistics. Statistics is all about understanding the data we already have in front of us. It's how we describe, summarize, and really find the shape of past events. Now, on the other side, we have probability. Probability is the language of uncertainty. It's how we navigate the totally unknown and predict the future based on what we've just learned. So the crucial takeaway here is that in machine learning, we use statistics to understand our training data, and we use probability to handle the uncertainty of making brand new predictions.
Let's start from the micro and work our way up to the macro, kicking things off with a concept you definitely already know, the mean. While it's just the average of a data set, in machine learning, this simple little metric is incredibly powerful. The mean acts as the foundational baseline for calculating error rates, figuring out feature weights, and generating normalization statistics. Without a really solid grasp of the mean, our models would just get completely overwhelmed by the sheer, raw scale of incoming data.
But hold on a second. What happens if one of those values in our data set isn't really like the others? Imagine we're cruising along with numbers like 10, 11, and 12, and then, bam, our data set suddenly swallows a massive outlier like 100. Just throwing that single number into the mix demonstrates the major weakness of relying only on the mean. If an AI uses a corrupted mean because of one extreme data point, its entire baseline for reality shifts. The model's average doesn't actually represent the typical value of our data anymore. It's been totally skewed by just one anomaly. Because the mean is so incredibly sensitive to those wild outliers, we need a backup plan in our statistical toolkit. Enter the median, which is simply the exact middle value of a sorted data set. Machine learning models rely heavily on the median because it is highly resistant to those outliers. Think about an autonomous driving system taking in noisy sensor data. If a sensor glitches and randomly reads an obstacle 1,000 miles away, the mean would absolutely panic. But the median? The median stays perfectly stable, ensuring robust, safe decision-making in a chaotic, real-world environment.
Okay, let's zoom out to the data set level now. Beyond just finding the center of our data, an AI really needs to know its shape, and that is exactly where variance comes in. Variance tells us how spread out the data points are from their mean. Are your data points packed tightly together, or are they just wildly scattered all over the place? Grasping variance is an absolute game changer in machine learning. High variance in your training data can lead to models that overfit, which essentially means the AI is just memorizing random noise rather than actually learning the true underlying patterns. And that leads us directly to standard deviation. Honestly, you could think of standard deviation as the more practical, everyday sibling of variance. It's just the square root of variance, giving us the typical amount of spread in the exact same units as our original data. Imagine two data sets that both have a mean of 50. Dataset A ranges super tightly from 48 to 52. Dataset B swings wildly from 10 all the way to 90. They have the exact same average, sure, but dataset B has a much larger standard deviation because that spread is just massive.
Now, what's really fascinating about this is how instantly standard deviation powers actual machine learning applications. The formula z equals x minus mu divided by sigma generates what's called a z-score. That sigma at the bottom, that is our standard deviation. In machine learning, we use this constantly for feature scaling and normalization. By dividing by the standard deviation, we scale completely different types of data, say a person's age versus their yearly income, so the AI can compare apples and oranges fairly, without the larger numbers completely dominating the neural network's math.
So we know how to look at one variable, but what happens when we compare two? This brings up a classic point of confusion: covariance versus correlation. Both look at how variables move together, but they have distinct specific jobs. Covariance basically just tells us the direction. do they move together or in opposite directions? But because it depends on the scale of the data, the resulting number could be literally anything. Correlation, on the other hand, is standardized. It tells us the direction and the strength of the relationship, always locking it neatly on a scale between -1 and +1. Simply put, covariance asks, do they move together? Correlation asks, exactly how strongly do they move together?
Actually, scratch that. Let's just pause for a second for a very quick, very emphatic reminder. Just because an AI finds a strong correlation between two things, it absolutely does not necessarily mean one caused the other. This is the golden rule when finding hidden relationships in data. For example, an AI reviewing hospital data once found that patients with asthma had a surprisingly lower risk of dying from pneumonia. The AI correlated asthma with a better outcome. Crazy, right? Having asthma obviously doesn't protect you from pneumonia. The reality was that asthma patients were immediately sent to intensive care, and that aggressive treatment saved their lives. We always have to interpret machine learning patterns with human context.
All right, so we've got a handle on the statistics side. Now let's transition to the second half of our mental model, the rules of machine uncertainty, otherwise known as probability. Probability simply tells us how likely something is to happen, and it always lives strictly between 0 and 1. 0 means impossible, 1 means absolutely certain. If you flip a fair coin, the probability of getting heads is 0.5. In modern neural networks, this is exactly what the softmax layer does. It takes raw, messy output scores and squishes them into clean, readable probabilities between 0 and 1, so the model isn't just giving a wild guess, it's giving a mathematically bounded confidence level.
To really get how AI makes complex choices, we've got to talk about conditional probability. This is probability based on prior information. Let's set up a quick little example. Imagine a classroom. There are 60 total students. 40 are boys, 20 are girls. And out of those 40 boys, exactly 10 of them wear glasses. Take just a second to lock those demographics in your mind. 60 total, 40 boys, 10 boys with glasses. Got it?
Now here is the conditional probability question I want you to think about. If I pick a student entirely at random, what is the probability of that student wearing glasses, given that we already know the student is a boy? That word given is the magic word here. It completely changes the game. We are no longer looking at the whole class of 60 students. By saying, given that the student is a boy, we've narrowed our entire universe down to just those 40 boys.
And boom, there's our answer, 25%. Since we know for a fact we are only looking at the 40 boys, and 10 of those boys wear glasses, the math is simply 10 divided by 40, which is 25%. This perfectly illustrates how prior information changes outcomes, and this is exactly what happens in AI. Every single time a self-driving car spots an octagon and decides it's a stop sign, or ChatGPT predicts the very next word in a sentence, it is fundamentally executing this exact given logic on a massive scale. It's constantly adjusting its probabilities based on the context it has already observed.
Now, as models process literally millions of these probabilities, this very specific, almost beautiful pattern starts to emerge, the normal distribution. You know this as the famous bell-shaped curve. It's entirely defined by two things we've already covered: the mean, which sits right at the peak of the bell, and the standard deviation, which dictates how fat or skinny that bell is. Normal distributions are everywhere in machine learning. They form the basis of Gaussian models and statistical inference, and they are crucially used to model sensor noise. Because natural errors tend to cluster right around the mean in this exact bell shape, AI can mathematically filter out the noise.
We are now reaching the absolute climax of probability in machine learning right here, Bayes' theorem. This is a mathematical formula that allows a model to update its belief when it receives new evidence. Amazingly, this concept comes from an 18th century reverend, yet it is now the core engine of cutting-edge AI. Think about a spam filter. Initially, the filter might think an incoming email is probably legitimate, but then it scans the text and sees the words urgent, wire transfer, and lottery winner. That new evidence radically changes the probability. Bayes' theorem is the exact math the AI uses to update its initial belief from safe to spam based on that brand new data. So let's tie this whole shebang together into a simple three-step pipeline. This essentially summarizes our entire explainer. Step 1, data. We use statistics, things like mean, median, variance, and standard deviation, to understand and structure the raw information. Step 2, uncertainty. We use probability, conditional probability, and Bayes' theorem to calculate the likelihood of different outcomes. And finally, step 3, prediction. We output a result. That pipeline, data to uncertainty to prediction, is the fundamental transition at the core of all artificial intelligence. Which brings us to our final takeaway.
When you ask an AI a question, it doesn't look up an absolute fact in some mystical database. It crunches the statistics, navigates the probability, and outputs something like this. I'm 92% confident this is a cat. Modern machine learning isn't about absolute, rigid certainty. It is highly educated, mathematical guesswork based on massive amounts of data. But it leaves us with a truly fascinating question. If AI is fundamentally just calculating probabilities, at what point does a 99.9% probability become indistinguishable from human intuition? Thanks so much for joining me on this explainer. Keep questioning the data, and I'll catch you next time.
Welcome to the Explainer. I'm your host, and today we're going to learn exactly why we absolutely must put our data under a magnifying glass before doing any machine learning whatsoever. If you've ever wondered why your predictive models are acting strange, or why an algorithm is kicking back completely baffling results, well, the answer almost always lies in what you didn't look at before you hit run. So today, we're becoming data detectives.
Let's dive right in with the absolute golden rule of machine learning. Do not train an ML model on data you haven't looked at. Seriously, treating your dataset like some sort of mystery box is a recipe for disaster. You wouldn't drive a car blindfolded, right? So why in the world would you train an advanced artificial intelligence model on information you haven't intimately explored yourself?
Here is our case docket for today. We'll quickly cover the golden rule, equip our visualization toolkit, hunt down some outliers, uncover hidden relationships, and then put it all together with the famous Iris case study.
All right, Section 1, the golden rule, and understanding our data before training. Let's look at why skipping straight to the shiny new models is a bad idea.
There is a really logical progression to our technical toolkit here. Usually, you start building your machine learning foundation with NumPy for your raw calculations. Then, you step up to Pandas for handling your datasets and structuring all those rows and columns. But step 3, visualization, that's the vital bridge. It's the ultimate tool for actually understanding what is happening inside those numbers before the machine takes over. Think about how our brains process information. If you're just staring at a massive spreadsheet of, say, student marks and the hours they studied, you might be able to guess a pattern if you stare at it long enough. But the second you draw a graph mapping those study hours against the marks, boom, the upward trend becomes instantly, undeniably clear. Visualization translates raw math into human intuition.
Moving on to Section 2, the visualization toolkit. Think of these tools as our magnifying glasses for data. We use specific tools like the popular Python library matplotlib to answer distinct questions. We aren't just randomly generating charts here, we're deploying them tactically. So, let's pull out our first magnifying glass with a highly specific question. How does a value change over an ordered sequence? If your data happens in a specific order, you need a specific tool to read it.
And the answer to that question is the line plot. It simply connects points with lines, and it's perfectly designed for when the order of values actually matters. Think about tracking temperature over time, sales over a few months, or a student's performance across different semesters. A line plot tracks the sequence so we can see exactly how something, like those student marks, generally goes up as study hours increase.
But what if order doesn't matter at all? What if we want to ask something completely different? Like, how are my values distributed? Say you've got a massive class and you want to know if most students are scoring between 60 and 80, or if the grades are just spread evenly across the board.
Well, we use a histogram for that. A histogram groups our data into ranges, which we call bins. This lets us see if the distribution is symmetric, narrow, or wide. Are there a ton of really low marks? Are they all bunched up right in the middle? A histogram instantly reveals the shape of your data, which tells your machine learning model what normal actually looks like for this specific data set.
Which brings us to Section 3, hunting down the outliers. Let's see how this all builds into finding the strange, hidden misfits in our data.
Because as data detectives, we have to constantly ask if there are clues that just don't fit the expected pattern. We need to know the general spread, sure, but more importantly, we need to know if there are highly unusual values lurking in the shadows.
Enter the box plot. It's designed exactly for this. It visually separates the normal spread, giving you the median and the quartiles right there inside the box from the extreme unusual values that sit way out on the margins. It's basically a built-in alarm system for anomalies. To really put this into perspective, imagine you're scanning through a data set of house prices. Everything is hovering right around $50,000. But suddenly, bam, you spot a $5 million mansion mixed in.
that single, massive number is an outlier, and it is actively ruining the reality of our data.
And that extreme example is exactly why finding outliers matters so much. That one $5 million mansion artificially drags the average price way up. It affects the mean, it changes the standard deviation, and it completely skews regression models. If we don't catch outliers with a box plot first, they will totally derail our machine learning performance, because the AI is going to try to learn a rule that accommodates a crazy exception.
Next on our agenda is Section 4, Finding Hidden Relationships. Now that we know the shape of our data and we've isolated the misfits, we have to figure out how different pieces of evidence connect to one another.
The most fundamental question before running any machine learning model is knowing if and how two features interact. Does feature A influence feature B? We plot individual points on a scatter plot to visually spot these relationships. If the dots form an upward slope, you've got a positive relationship. If they slope downward, it's negative. If it just looks like a massive cloud of random dots, no linear relationship. This is essential for predicting outcomes. Though, as good detectives, we always have to remember the golden rule of statistics. Correlation does not automatically mean causation. Just because two things move together doesn't prove one caused the other.
But what if we have a dozen variables? You really can't look at 100 scatter plots easily. To look at everything all at once, we use a correlation matrix table. This measures how strongly numerical variables are linearly related, with values ranging from -1 to +1. Look at hours and marks. They have a 0.9 correlation. That is an incredibly strong positive relationship. And notice how a variable compared to itself is always a perfect 1.0. Often, we use Python tools to shade these matrices, so darker shades mean stronger correlations, letting us spot predictive relationships in literally seconds.
All right, Section 5, the iris case study. Let's bring all these tools together for a practical investigation using the famous iris flower dataset. It's a total classic starting point for machine learning.
So, imagine we want to train an AI to identify flower species. We run our iris investigation. We use a histogram to see where the sepal lengths are mostly distributed. We use a scatter plot to see if a flower's sepal length and width are related to each other. We drop a box plot to find the median spread and check for any mutant outlier flowers. And finally, we generate a correlation matrix to see which numerical measurements strongly correlate. By asking these exact questions and generating these plots, we discover the precise relationships that will be incredibly useful for predicting the flower species later on.
This right here is the ultimate toolkit summary. You have one dataset and you ask 5 fundamental questions. You want to know distribution? Use a histogram, relationship, scatter plot, trend, line plot, outliers, box plot, feature relationships, correlation matrix. Data visualization isn't about making pretty graphs for a boardroom presentation. It is a rigorous, investigative framework to truly understand your data before you ever try to build a model.
So before you rush to type out the code to train your next predictive algorithm, I want you to ask yourself this. Is your data truly ready for AI, or are you flying blind? Machine learning will happily learn the exact wrong lessons if you feed it noisy, misunderstood data. What hidden truths or lies are hiding in your dataset right now? Equip your magnifying glass, be a data detective, and find out before the machine takes the wheel.
Welcome to This Explainer. Today, we're diving straight into the fascinating world of dimensionality reduction, specifically tackling what's often called the daunting 100-feature problem. We're going to do this by unpacking a wildly powerful technique, principal component analysis, or PCA. Honestly, if you've ever stared at a massive data set with endless variables and just felt totally overwhelmed, well, you're in exactly the right place.
Let's kick things off with a massive paradox. How on earth can we squash 100 complex features down to just 2 or 3 without completely losing the plot? I mean, think about that for a second. We're talking about taking an immense amount of data, stripping away literally 97% of the dimensions, and somehow still keeping the core information intact. It sounds crazy, right? How is that even mathematically possible? Well, that is the exact riddle PCA solves.
Here's our roadmap for today. We'll start with the 100-feature problem. Unpack variance and components, see exactly how PCA compresses data, compare transformation versus selection, discuss when to actually use it, and finally, get you set up with a mini project.
All right, let's jump straight into Section 1, the 100-feature problem.
Okay, so to really get this, let's look at a completely overwhelming yet highly relatable scenario involving student data. Picture a data set where you've got students, and for each one, you have tons of features. We're talking age, study hours, scores for Test 1, Test 2, Test 3, attendance, the whole shebang. Now, if we only have one feature, let's say age, it's easy, right? We just visualize it on a simple 1D line. Toss in a second feature, like study hours, and boom, we can plot a nice 2D scatter graph. Throw in test 1 scores, and we can still mentally picture a 3D cube of data. But what happens when you have 100 features per student? 100 dimensions are literally impossible for our human brains to picture. It's just a giant wall of numbers. And that's exactly where PCA steps in. Its whole goal is to find a smaller number of dimensions that preserve as much useful variation in that massive table as humanly possible.
Moving on to Section 2, let's unpack variance and components.
To fix this whole visual nightmare, we first need to wrap our heads around what PCA is actually looking for, and that is variance. Think of variance simply as the spread of the data. Take dataset A, for instance, where every single number is a 5. There is virtually zero variation there, which means incredibly low variance. Now compare that to dataset B, 1, 3, 5, 8, and 12. These numbers are much more spread out, giving us high variance. PCA absolutely loves high variance. It actively wants to find the directions where our data has the most spread, exactly like dataset B. Why? Because that spread holds all the juicy information. I mean, if a feature never changes, it tells us absolutely nothing new about our subjects, right?
Which brings us to the hero of the day, the principal component. A principal component is essentially a brand new, optimal angle to view our messy data cloud. Instead of using your original features as the standard axes on your graph, PCA essentially rotates the entire coordinate system. It slices right through the thickest, most variant parts of your data. Think of it like shining a flashlight at a weirdly shaped object in a dark room. You want to cast the widest, most detailed shadow possible to figure out what it is.
So under the hood, PCA is basically asking a series of questions to find these new directions. First up, it asks, okay, what direction contains the absolute most variation? And boom, it creates PC1. Once it has that, it asks, all right, what's the next most informative direction? And creates PC2. But here's the catch. PC2 has to capture that next largest amount of variation while being strictly perpendicular or orthogonal to PC1. Then comes PC3, following the exact same rules, and so on. It's literally ranking these new axes strictly by how much information they carry.
All right, Section 3, how PCA actually compresses data.
Let's explore how these newly found principal components pull off the magic trick of data compression. Spoiler alert, it all comes down to redundancy. Imagine you have a data set where students who score high in math usually also score high in physics. Because these two features tend to move together, they're highly correlated. They're carrying similar, overlapping information, while PCA recognizes this. Instead of keeping both math and physics as two totally separate dimensions, it finds a new direction that captures their shared success, combining them into one with almost zero information loss.
And honestly, this happens all the time in real-world data. Height in centimeters versus height in inches, arm length versus leg length, weight versus BMI. Just like these physical body measurements, when 100 features are highly correlated, PCA discovers a few underlying directions instead of needing them all separately. You just don't need 100 distinct axes when they are all essentially whispering the exact same underlying secrets about the data.
This brilliantly illustrates the true power of explained variance. Say you started with 100 features. PCA might crunch the numbers and determine that your first new component, PC1, explains 60% of the variance in your entire dataset. Then PC2 might explain another 30%. Add those up, and by keeping just 2 new dimensions, you've retained 90% of the explained variance. You literally just compressed 100 dimensions down to 2 while sacrificing a measly 10% of the information. That is the absolute magic of PCA. Just a quick caveat though, it entirely depends on your specific dataset. It doesn't guarantee 100 features will always compress this beautifully, but when your data is highly correlated, it's incredibly effective.
Which leads us nicely into Section 4, transformation versus selection.
Now, before you go running off to apply this to every dataset you own, we really need to clarify what PCA is actually doing under the hood, and crucially, what it needs from you to work properly. Listen to me on this one. You absolutely must standardize your data first. Think about it. Salary might be measured in the tens or hundreds of thousands, right? While age is usually just a 2-digit number. Remember how we said PCA hunts for the largest variance? Well, if you don't scale or standardize your data, PCA is going to look at a salary of 80,000 and an age of 30, and it will give way too much importance to salary simply because the numbers are physically larger. It'll think salary has massive spread, while age has almost none. Standardizing puts everything on an equal playing field, ensuring PCA finds the true mathematical variation, not just large numerical scales.
It is also vital to remember what PCA fundamentally is. It is not feature selection. Feature selection is when you look at 100 original features and simply cherry-pick your top 10 favorites. You're just choosing from what's already there. PCA, on the other hand, is feature transformation. It creates brand new features from scratch. Your new PC1 isn't just age or salary. It's a complex mathematical combination of age, salary, study hours, and everything else, all rolled up into one brand new axis.
Moving into Section 5, let's talk about exactly when to use PCA.
The most crucial skill here is knowing exactly when to deploy this bad boy in your machine learning pipeline and when to just leave it in the toolbox. In practice, if you're using standard libraries like scikit-learn, your workflow is going to look like this. Step 1. Standardize your data so all scales are equal. Step 2. Apply PCA to shrink those dimensions down to just the components that capture the absolute most variance. And Step 3. Feed those new principal components, not your original messy data, straight into your machine learning model. It really is a clean, hyper-efficient pipeline.
So when do you actually want to use this pipeline? Well, you'll definitely want it when you have a ton of redundancy in your data. It's absolutely fantastic when you want to visualize a 50-dimensional dataset in a simple 2D or 3D scatter plot, just to see if there are any hidden clusters that weren't obvious before. It is also incredibly useful when you need to drastically reduce computational complexity. I mean, your algorithms will train so much faster and honestly often perform better with fewer dimensions and a lot less noise.
However, you need to stay far away from PCA if you absolutely must be able to explain your model using the original unchanged features. Remember, PCA creates mathematically blended combinations. If your boss asks you why the model made a certain prediction, looking them in the eye and saying, because of PC1, isn't exactly going to fly if they need to hear because of their age and salary. Also, if your dataset is already super small, or if the variance you're discarding actually contains the specific anomaly you are hunting for, just skip PCA entirely.
Finally, we've reached Section 6, your PCA mini project. Let's see how all this theory builds into something you can actually test yourself today. Because honestly, to truly grasp this without just blindly memorizing math equations, you need to get hands-on. So here's your mini project. Take the famous iris dataset. First things first, standardize the data. Next, apply PCA to reduce it down to exactly 2 components. Finally, plot those points on a simple scatter graph. You are going to see how an otherwise unvisualizable dataset suddenly transforms into clear, beautiful, distinct clusters of flowers right before your very eyes.
I'm going to leave you with this final challenge as you dive into your coding environment. Once you actually compress that data and create your visual masterpiece, check the underlying numbers. Exactly how much variance did your top 2 components manage to save? Finding that percentage is the ultimate key to understanding the sheer power of dimensionality reduction. If you can mathematically compress the total chaos of the natural world into just 2 dimensions, what other hidden truths are waiting to be uncovered in your data? Until next time, keep exploring.
Okay, let's dive right into this. Welcome to the Explainer. Today, we're opening up our machine learning toolkit to dissect something really fascinating: k-means clustering. We're going to explore exactly how this algorithm acts as our ultimate tool for finding hidden mathematical structures in messy, completely unlabeled data.
But before we get into the actual mechanics of it, I want you to consider this. How do you find patterns when you don't even know what you're looking for? Really think about that. It's kind of the ultimate data mystery. Imagine being handed a massive spreadsheet with thousands of rows of information, but absolutely nobody has given you the answer key beforehand. There's no column telling you, hey, this is a good customer, or this is a bad customer. It's literally just raw numbers. Trying to make sense of that kind of information manually? Yeah, it's nearly impossible.
So, to solve this mystery today, here's how we're going to break it all down. First, we'll tackle the unlabeled data problem head-on. Then we'll meet our star player, k-means, and its trusty centroids. After that, we'll walk through how the algorithm actually works step by step, figure out how to choose the magic number k, and finally, we'll apply it all to some real-world customer segmentation.
All right, let's jump straight into part 1, the unlabeled data problem.
You know, in supervised learning, you already know the answer. You feed the computer an input and a known label, and it basically learns to predict that label for future data. It's a lot like having a teacher grade your test, right? But unsupervised learning, that operates with absolutely no labels.
The algorithm is like a detective walking into a crowded room full of complete strangers. The goal isn't to predict a specific label because, well, there isn't one. The goal is just to observe the room and find the natural groups organically.
Let's say we have 5 customers, along with their annual income and a spending score. Just staring at this handful of records, we might intuitively start to see some patterns, but imagine scaling this up to 1,000,000 rows. K-means is going to look at this exact type of raw data and automatically discover the categories for us. Without us ever having to label a single row, it's going to figure out that some customers belong to a low-income, low-spending group, while others belong to a high-income, high-spending group.
Which brings us to our second topic, meet K-means and centroids.
So, the entire K-means algorithm revolves around this concept of the centroid. Mathematically speaking, it's simply the center, or the average position, of all the data points in a particular cluster. And this brilliantly illustrates how the algorithm physically groups data together. Think of the centroid as a really powerful magnetic anchor. Wherever you drop this anchor, it just pulls all the closest data points right toward it, claiming them for its cluster.
But you might be wondering, how does a data point actually know which centroid it's closest to? Well, the algorithm has to measure it. And hey, don't let the math formula intimidate you here. This is just Euclidean distance. It's simply calculating the good old straight line distance from point A to point B. For instance, if a data point is at coordinates 2, 3, and a centroid is sitting at 5, 7, you just plug those numbers in. It's the difference in the x's squared plus the difference in the y squared, take the square root, and boom, you see that the distance is exactly 5. This one simple calculation is literally the heartbeat of K-means. It's just constantly asking, how far am I from the center?
Okay, let's move on to part 3, how K-means actually works in practice.
K-means follows this beautifully simple, repetitive 4-step loop. Step 1, it calculates the distances from every single data point to the initial centroids that we've randomly dropped in. Step 2, it assigns each point to whatever centroid is closest. Step 3, now that the points are grouped up, it calculates the new average position of those groups and literally moves the centroids to that new center. And then step 4, it just repeats the process. Because the centroid moved, the distance is changed. The algorithm is constantly reassigning points and dragging those magnetic anchors around over and over again until they settle naturally and just stop moving. That's exactly when you know your clusters are finalized.
So that sets us up perfectly for part 4, choosing the right number K.
Now, what's really interesting about this is the core optimization problem of the whole algorithm. Remember, the K stands for the number of groups. But if you have no labels to begin with, how do you know if K should be 2, 3, 4, or 5? It's a Goldilocks problem. If you pick too few, you mash completely different groups together. Pick too many, and you artificially slice up groups that should naturally be together. We need a solid way to mathematically determine that ideal number.
The most famous way to solve this is called the elbow method. When you test out different values for K, you calculate the clustering error, which is basically just how tightly packed your clusters are. If you plot this on a graph, the error will always drop as you add more clusters, but the absolutely crucial part is how fast it drops. You want to find the elbow point on that curve, the exact crease where the massive improvements in error start drastically slowing down and flatlining. That elbow indicates you've essentially found the natural breaking point of your data.
But, the elbow method isn't always foolproof on its own, so we also rely on something called the silhouette score. Testing K at 2, 3, 4, and 5 reveals how perfectly each point fits inside its own cluster compared to neighboring clusters. Higher is better here. In this scenario, setting K to 3 gives us a score of 0.67, which is clearly the highest. This tells us mathematically that at exactly 3 clusters, these data points fit brilliantly inside well-separated groups.
To summarize this whole verification process, just keep this simple distinction in mind. The elbow method is all about looking inward, measuring how much the clustering error decreases as we add groups. The silhouette score, on the other hand, is about looking outward, measuring how well separated our clusters are from each other. Using both of them together is how we confidently verify our detective's findings before we present them to anyone.
Finally, let's bring it all together in part 5, real-world customer segmentation.
Before we run the numbers, I have to give you a massive warning. This is absolutely crucial. Let's say a customer's income is around $100,000, while their age is 25. Because K-means relies purely on distance math, 100,000 is going to completely overpower 25. The algorithm will essentially treat a 25-year-old and an 80-year-old as the exact same person just because their incomes are similar.
To fix this, you must always scale or standardize your features before using k-means. You have to put everything on a level playing field first.
Once you've safely scaled your data and run it through a tool like Python scikit-learn, you might end up with clusters like these: low value, careful, premium, and moderate customers. So the really mind-blowing point here is this: you never told the computer what a careful customer was. You didn't give it any of those labels. The algorithm discovered these 4 highly distinct groups automatically, purely based on mathematical similarity from completely unlabeled data. And that leads us perfectly to our final, most powerful mental model to take away today. K-means doesn't know what a customer segment is. It only sees distances. You interpret what each cluster means. The algorithm flawlessly groups the math for sure, but it's ultimately up to human intuition to assign that business value. It really makes you wonder, doesn't it? If an algorithm can group data this efficiently, what other hidden truths are sitting right now in your own raw data, just waiting for the right math to reveal them? Thanks so much for joining me on this explainer. I hope you found it as fascinating as I do.
All right, let's just jump right in. You know, when we hear the term machine learning, it is so incredibly easy to picture, well, some kind of futuristic magic, right? Like some mysterious black box where you toss in raw data and perfect answers just magically pop out the other side. But what if I told you it's actually way simpler than that? Honestly, just think of a computer acting exactly like a student who is desperately trying to study for a massive final exam, complete with the late-night data cramming. It's not magic at all. It is literally just a process of learning to find patterns in data so it can pass a test. So welcome to this explainer. Today we're going to break down exactly how machine learning patterns work, completely from the ground up.
Okay, so here's our roadmap for this explainer. We're going to cover 1. The AI family tree. 2. Finding the hidden patterns. 3. Anatomy of the data. 4. The machine learning exam. 5. Memorizing versus true learning. And finally, number 6, the complete learning pipeline. Let's do this.
Starting off with Section 1, the AI family tree, mapping the universe of intelligence.
Before we zoom in on the details, we really need to understand the big picture of where machine learning actually lives. So the absolute broadest category out there is artificial intelligence, or AI. This is the biggest concept in the family tree. AI simply means making machines perform tasks that would normally require human intelligence. We're talking about things like reasoning, planning, making decisions, understanding language, computer vision, robotics, the whole shebang. It's basically the giant overarching umbrella that covers literally everything else we're about to talk about.
Now, go one layer deeper, and we find machine learning, or ML. This is a specific subset of AI. And guys, this is where a massive paradigm shift happens. Because instead of a human programmer sitting down and explicitly hard-coding every single rule, like typing out, if X happens, then do Y, we do something totally different here. We give the machine a massive pile of data, and we just allow the model to learn the patterns all on its own. We are literally teaching by example rather than by rigid instruction.
And then finally, at the very bottom, we have deep learning, or DL. This is a further subset of machine learning, and it's based primarily on multi-layer neural networks. When you hear about those really complex AI tasks like convolutional neural networks processing images or transformers writing text, yeah, that's deep learning. But here's the crucial takeaway for us. AI is the broad universe. Deep learning is the deepest layer. But our focus for this explainer is planted squarely on that incredibly powerful middle layer, machine learning.
Moving on to Section 2, finding the hidden patterns, or how the machine studies. Because just like human students, machines have different ways of actually studying the material. And there are 2 main study styles here. First, on the left, we've got supervised learning. This is basically like studying with an answer key. We give the model the inputs, and we give it the correct answers. So for example, if we want to build a spam detector, we feed it a bunch of emails and explicitly tell it, hey, this one is spam, but this one over here is safe. It learns the direct relationship between the input and that known output. But then on the right, we have unsupervised learning. And this is much harder because we don't provide the correct answers at all. No answer key. Imagine handing the machine raw customer data with absolutely 0 categories and just saying, figure it out. The algorithm has to hunt down hidden patterns entirely on its own, like maybe discovering that your customers naturally cluster into 3 distinct purchasing groups. So supervised means learning from answers. Unsupervised means finding patterns completely in the dark.
Now, there is a third, totally different approach called reinforcement learning. With this one, an agent interacts with an environment and learns purely through trial and error, using rewards and penalties. Think of an AI learning to play a video game. Over thousands of attempts, it learns which actions score points. Those are the rewards, and which actions make it lose a life, the penalties. It's an incredibly powerful way to train robotics and autonomous systems.
All right, Section 3, Anatomy of the Data. Let's look at the study flashcards.
So what exactly does the machine look at when it's trying to learn these patterns? Well, suppose we want to predict whether a student will pass a class. Take a look at the first 3 columns in this dataset: hours studied, attendance, and previous score. In machine learning, these inputs have a specific name. They're called features. They're just the input variables the model uses. Then, look at that final column on the far right, result, which either says pass or fail. This is called the label. The label is simply the expected answer we're trying to predict. So to sum it up, features equal your input, and the label equals your expected output. These rows are basically the digital flashcards our machine is going to use to study.
Section 4, the machine learning exam. Training, validating, and testing.
Okay, so how do we take those flashcards and put our model through a really rigorous academic semester? This workflow is absolutely crucial to understand, because we don't just dump all our data into the machine at once. No way. We actually split it up into 3 distinct phases. Step 1 uses the training data. This is where the model actually learns. It looks at the features, looks at the labels, and it adjusts its internal weights and parameters to get better and reduce its errors. Step 2 uses the validation data. Think of this step like taking a series of practice quizzes. We use this data while we're building the model to tune our settings, compare different choices, and basically just make sure we're on the right track. And finally, step 3 uses the test data. This is the final exam. This data has to remain completely, 100% unseen by the model until the very end to give us a true, unbiased evaluation of how well it actually learned the material.
Which brings us perfectly to Section 5, Memorizing versus True Learning. Let's talk about the trap of overfitting.
We seriously need to talk about the absolute biggest trap our digital student can fall into. I want you to think about this question for a second. If we want our model to be as smart as humanly possible, why can't we just train it on every single piece of data we have? Like, why bother holding back this test data at all?
Well, here is exactly why. Think about a student who simply memorizes the practice questions word for word. Sure, they might get 100% on a practice quiz, but they are going to totally bomb a real exam that asks new questions. Why? Because they didn't actually understand the underlying concepts. In machine learning, this major warning sign is called overfitting. That's what you're seeing on the left. The model essentially memorized the training data instead of learning general patterns. What we really want is on the right, generalization. We want the model to perform well on new, completely unseen data. That is what true understanding looks like. And that, right there, is exactly why keeping our test data completely separated is absolutely critical.
Section 6, the complete learning pipeline. Let's put it all together.
Okay, let's take everything we just talked about and build a real-world scenario. Imagine we're building a computer vision model to predict if a student is actually engaged with their screen. First, we extract our features, things like gaze direction, face presence, head pose angle, and facial expression. Those are our imports. And our label is whether they are engaged or not engaged. We take a massive data set of these rows, we feed a big chunk of it into our pipeline as training data so the model learns the weights, we tune its settings using our validation data, and finally, we prove that it actually generalizes by testing it on fresh, unseen test data. The features beautifully map to the labels, and boom, we've created a functional, predictive machine learning model.
To permanently cement this in our brains, let's just do a rapid review of our core cheat sheet. AI is the broad concept of making machines intelligent. ML is specifically about learning patterns from data. DL uses deep neural networks. Features are your inputs. Labels are your expected answers. Training is where the model learns as parameters. Validation is where you tune the model. Testing is your final unbiased evaluation. Overfitting is the massive trap of just memorizing the training data. And generalization, the ultimate goal, is achieving true understanding that actually works on unseen data. By framing machine learning not as some impossible magic, but as a structured pipeline of teaching a system to find patterns and features to predict a label, the whole black box finally starts to make sense. But it does leave us with a pretty fascinating thought. If a machine can successfully learn the hidden, super complex patterns of something as subtle as student engagement, what unseen patterns could it find operating silently in your own daily life? Thanks for exploring this explainer with me today. Keep asking questions and definitely keep looking for those patterns.
Hey everyone, let's jump right into this explainer. Today, we're exploring something super fascinating, how we can actually leverage the structural efficiency of nature to make high-level predictions. We're talking all about tree-based machine learning algorithms, and specifically, how trees help us make predictions. Now, our goal today definitely isn't to just memorize a textbook full of definitions, right? Because honestly, that doesn't help you at all in the real world. Instead, we want to look at a dataset and ask one absolutely crucial question. Why would I choose a specific algorithm for this exact problem? Imagine having a dataset and 6 totally different ways to solve it. We need to build a mental model so you instantly know which mathematical tool to grab.
Section 1, the simple decision tree.
Okay, so the decision tree is literally the seed and foundation for everything we're looking at today. The intuition here is incredibly simple. The algorithm just keeps asking questions until it can make a confident prediction. Think about it like this. Say we want to predict whether a student will pass or fail a class. The logic is highly intuitive. You look at a feature, like say their attendance record. Is it over 80%? If that condition is true, go left. Otherwise, you go right. You just follow these branches down, checking different conditions step by step until you hit a final prediction. Now, what's really awesome about this approach is just how incredibly interpretable it is. Decision trees are fantastic because they seamlessly handle both numerical data, like test scores, and categorical features, like a student's major. But their absolute biggest advantage? They are ridiculously easy to understand and visualize. It's totally perfect for when you need to clearly explain the rules behind a decision to a client or stakeholder, because you can literally trace the exact path of the decision. But there is a catch. The main problem is that a single tree tends to overfit. Basically, that means it might just memorize the specific training data you give it, instead of actually learning the general patterns that apply to new, unseen data. And that naturally leads us right into our next structural evolution, moving from a single tree to the random forest. Section 2, growing a random forest. So to build out from a single, sometimes flawed decision maker into a really powerful collective consensus, we turn to the random forest. I absolutely love this analogy from our source material. Instead of asking one single tree for an answer, we ask many different trees. Imagine 100 doctors independently diagnosing a patient. Each tree gets a random sample of training data and a random subset of features, so they all have a slightly different perspective. By combining all these weak or varied models, you get one much stronger, highly reliable prediction. It's incredibly robust for predicting complex things like loan approvals, and you don't even need extensive, painstaking tuning. It really excels at tabular datasets and handles a massive amount of features beautifully. You do make a trade-off, though. You trade away some of that easy interpretability we loved in the single tree, and it's definitely computationally heavier since, you're now crunching numbers for an entire forest. Section 3, gradient boosting and mistakes. All right, gradient boosting is kind of the ultimate evolution of tree-based prediction, and it's a massive cornerstone of modern machine learning. The absolutely crucial point here is how this differs from the random forest. Instead of a parallel vote where all the trees are independent, gradient boosting builds small decision trees sequentially. So you build a weak model, look closely at where it made mistakes, and then build the next tree focusing entirely on correcting those specific errors. Then you just repeat that process, continuously learning from your mistakes step by step. This sequential error correction yields truly mind-blowing performance on complex, nonlinear tabular data. You've probably heard of super popular implementations of this, like XGBoost or LightGBM. They're famous for literally dominating data science competitions. It's incredibly powerful, though you absolutely have to control its hyperparameters carefully so it doesn't overfit and just end up memorizing the random noise in your data.
Section 4, beyond the ML forest.
Now, while trees are fantastic, a practitioner always has other tools in their toolkit, right? So let's step out of the forest for a second and look at a few alternative ways to view the exact same dataset, starting with K-nearest neighbors, or KNN. This algorithm classifies a new example by simply looking at the closest surrounding examples. It basically asks, hey, show me the nearest data points and I'll just copy what they're doing. Because it relies so heavily on distance, feature scaling is super critical here. It's a really great choice for smaller datasets where nearby observations naturally tend to share similar outputs.
Next up is the support vector machine, or SVM. This one is brilliant at finding the safest possible boundary between different groups in your data. It doesn't just draw some arbitrary line. It actually looks for the largest margins separating the classes. It's particularly useful for high-dimensional tasks, a classic example being separating spam emails from your normal inbox.
Finally, we have naive Bayes. This algorithm uses probability to ask, given these features, which class is most probable? Now, it's called naive because it makes a pretty strong assumption that your features are conditionally independent. But hey, even if that isn't perfectly true in reality, it's still an extremely fast and attractive choice, especially for classifying text, documents, and doing things like sentiment analysis. Section 5. Choosing the right algorithm.
So, bringing this all together, the real skill isn't just knowing these algorithms exist. It's selecting the exact right tool based on the specific shape and size of your data. Think of this as your ultimate mental cheat sheet, mapping the basic intuition of each algorithm directly to its strongest use case. Remember, don't just memorize definitions, memorize these associations. Random forest is for many trees voting, SVM finds the safest boundary, and gradient boosting is all about step-by-step correction.
When you're facing a brand new problem, you should always be asking yourself these practical questions. How much data do I actually have? Is it text? And crucially, do I need pure interpretability? Because if you need to explain your logic to a stakeholder, a simple decision tree might be far more valuable than a super complex gradient boosting model, even if the latter happens to be slightly more accurate. To really cement this, you should try putting it into practice with a mini project. Take a simple data set, maybe something measuring student performance, and train our 3 tree-based models on it: a decision tree, a random forest, and gradient boosting. Run them side by side and see exactly how they scale in real time and how their outputs differ from one another. I'll leave you with this final thought to explore further. When you run that test, the most important question isn't simply which algorithm has the highest accuracy. It's actually, why did this algorithm perform better or worse on this specific data set? Asking why an algorithm worked is the secret step that moves you from being just a coder to a true practitioner. As you analyze your results, ask yourself, if the gradient boosting model fails spectacularly where the simple decision tree succeeds, what is your data secretly trying to tell you? Thanks for joining me on this explainer. Keep asking those big questions, and happy building.
Welcome to This Explainer. Today, we are diving straight into the mathematical engine of neural networks to figure out exactly how they learn. You absolutely don't need to be a calculus expert to follow along here, but grasping the logic behind weight updates, that changes absolutely everything about how we view model training. So, let's jump right in.
So how do neural networks actually learn from their mistakes? Well, to understand how an AI model corrects its errors, you kind of have to imagine standing blindfolded on a massive mathematical mountain, just trying to find your way down. You can't see the bottom of the valley at all. You can literally only feel the angle of the ground directly beneath your feet. In this sort of blind environment, networks use a very specific mathematical logic for their weight updates, navigating down that mountain step by step.
Let's start with the absolute basics. At its core, a machine learning model is essentially just a function. Kind of like y equals x squared back in high school math. It takes an input, applies some math using parameters like weights and biases, and then it maps that input to a prediction. But, what happens when that prediction is just completely wrong? When the model makes a mistake, we measure that error using a loss function. You can visualize this loss function as a giant bowl where our ultimate goal is to reach the lowest possible point. The function calculates the difference between the actual value and the model's predicted value. The very bottom of that bowl is where the error is the smallest, and our entire objective is to minimize that loss.
To find our way down to the bottom of this error bowl, we have to know the slope. And that is exactly where the derivative comes in. It tells us the exact angle of the hill right where our current prediction is standing. It basically answers a vital question. How quickly is something changing right here, right now? If a function's derivative is, say, 6 at a specific point, it means the slope of the hill is increasing pretty sharply right under our feet. However, since machine learning models have many parameters, sometimes billions of them, not just one, we use partial derivatives to figure out what happens to our loss if we tweak just one specific weight. A partial derivative isolates the change. It allows us to ask, okay, what happens to the overall error if I adjust weight number 1, but keep weight number 2 and weight number 3 completely frozen in place? But what happens when we combine all those isolated measurements? Well, when we gather the partial derivatives for thousands or millions of individual weights together into one single matrix, we get what is called the gradient. The gradient is simply the complete collection of all those individual slopes, all bundled into one place. So the crucial point to remember here is that while a standard derivative gives you the slope for just one variable, a gradient acts as a massive compass, pointing out the slope for every single parameter at once.
For a neural network containing millions of weights, the gradient tells us exactly how the loss changes with respect to all of those weights simultaneously. It's a real game changer.
Because neural networks are really just layers of functions chained together, we can actually step backward through them. Using the chain rule, we multiply these gradients in a chain reaction. By multiplying the individual derivatives together, we can figure out exactly how a tiny change at the very beginning of the network impacts the final loss at the very end. This right here is the mathematical foundation of backpropagation.
And this brings us to the climax of our explainer, and honestly, the core problem of gradient descent. If we adjust a weight, how do we absolutely guarantee we are moving downhill? We've gathered all this math to figure out the slope of the mountain, right? But how do we actually update the model's memory to ensure the error goes down rather than accidentally climbing up and making things worse?
The answer lies in what is arguably the most important equation in machine learning, which plainly translates to this: your new weight equals your old weight minus the learning rate multiplied by the gradient. This single, elegant equation is the fundamental engine driving how machines actually learn from data. Let's break down exactly why it works so well.
The real hidden magic here, it's literally that minus sign. Because the gradient always points toward the direction of increasing loss, subtracting it forces our model to step backward, moving strictly downhill. The math naturally tells us which way is up, so we intentionally do the exact opposite to go down.
Let's look at the numbers to put that into perspective. For example, if our old weight is 5, our step size is 0.1, and we have a positive uphill gradient of 2, we take 5, subtract 0.1 times 2, and boom, our new weight is 4.8. It perfectly moves us down the slope, safely closer to the bottom of the bowl.
Alternatively, what if we're on the other side of the bowl with a negative gradient of 3? Well, subtracting a negative creates a positive, right? So that increases our weight to 5.3. This proves the equation automatically corrects itself no matter which side of the hill we're standing on. You don't have to manually tell the model whether to increase or decrease the weight. It hits the nail on the head every single time.
That step size multiplier we just used is called the learning rate, and it controls exactly how far down the hill we jump with each and every weight update. It determines the sheer size of the step the model takes in the opposite direction of the gradient. Choosing this step size is a super delicate balance. If it's too small, your model learns agonizingly slowly, taking literally forever to reach the bottom. But if it's too large, it might jump completely out of the bowl and fail to converge at all. A perfectly tuned learning rate moves the model toward the minimum error efficiently and safely. When you put the whole shebang together, it becomes clear that you really don't need a degree in advanced calculus to build an AI. You just need to understand how these core concepts map together physically. Functions map inputs, derivatives measure change, the gradient gathers all those changes up, the chain rule propagates them backwards through the layers, and finally, gradient descent actively uses those gradients to relentlessly reduce the error.
Now that you possess this key mental model, that gradient descent simply finds the uphill slope and deliberately turns around, complex AI architectures suddenly become incredibly intuitive. But if this single, simple equation can optimize millions of parameters to recognize faces or write code, what happens when we start letting AI optimize its own learning rate? We'll leave you to think about that one. Thanks for joining us for this explainer.
Welcome. Today, we're going to do something pretty incredible together. We are diving deep to demystify the underlying mathematics of artificial intelligence and neural networks. Look, if you've ever stared at machine learning and thought, wow, that is just an impenetrable black box, well, you are exactly in the right place. This explainer is all about taking the intimidation completely out of AI. How? By unlocking the master equation that powers the whole shebang. Let's get into it.
Okay, let's dive right into this. A neural network is not magic. I know it feels like it sometimes, but it's not a sentient brain, and it is definitely not wizardry. At its absolute core, an AI is really just a sequence of highly organized mathematical operations. It's just math. And once we understand the basic vocabulary of that math, the curtain is pulled back and the magic trick is completely revealed. And here is the trick. Here is the master key to the whole kingdom. Y equals WX plus B. This beautifully compact single equation is literally the fundamental engine behind neural networks. I mean, it looks so simple, right? But the way these four little symbols interact, that is exactly what allows a computer to recognize a face in a photo, translate languages, or even predict the stock market. So today, we are going to completely deconstruct this engine, piece by piece, until you understand exactly how Y equals WX plus B actually runs. So, here is our roadmap for today. 1. The master AI equation. 2. Meet the building blocks. 3. The math in motion. 4. Assembling the neural network. And finally, number 5, the big picture. All right, starting off with section 1, the master AI equation. That underlying language? It's linear algebra. Think of it kind of like this. As humans, if we want to look at data, we might load up a pandas dataset or open a massive Excel spreadsheet to understand it visually, right? But computers, well, they don't have eyes. Linear algebra is the mathematical language they use to represent that very same data and perform calculations inside the machine learning model. It is, quite literally, exactly how the AI understands and processes the world around it. Moving right along to section 2, meet the building blocks. Let's meet our first character, and it is the absolute simplest of all, the scalar. A scalar is really nothing more than a single number. That's it. For example, if we have a student and their age is 20, that number 20, that's a scalar. Or in the context of machine learning, a learning rate is a scalar. But most importantly for us today, the scalar represents the b in our master equation, y equals wx plus b. That b stands for bias, and it is just a single number we add at the very end of our calculation to adjust the final result. Next up, we have the vector. Now, if a scalar is just one number, a vector is a collection of numbers arranged in one direction, basically like a list. So why do we actually need this? Well, suppose we want to represent that same student, but just knowing their age isn't enough. We want to track their study hours, their sleep, and their past marks. Instead of keeping 3 separate disorganized values floating around, we neatly group them into a single list. We call this a feature vector. And going back to our master equation, this represents the x. The x is our input, the actual tangible data features we're feeding straight into the model. Progressing from there, on one side, we have our 1D vector, which organizes the list of features for one single student. But what if we have a whole classroom? Well, we upgrade to a 2D matrix. Think of this as a grid representing multiple students and multiple features all at once. Typically, the rows represent our individual samples, like the students, and the columns represent the specific features we are tracking for them. It's like upgrading from a single line of data to a full spreadsheet. Formally defined, a matrix is a collection of numbers arranged in those rows and columns we just talked about. It allows us to represent a whole data set. But honestly, its most critical role in AI is representing the W in our master equation. The W stands for weights, and weights are basically the strength of the connections inside a neural network. It's literally what the AI is actually learning during its training phase. By organizing these weights into a matrix, the computer can super efficiently multiply them against our input vectors. Which brings us to section 3, the math in motion. Let's see how these pieces interact. So when we want to combine our feature vector with our weight matrix, we don't just mash them together randomly. No, we use an operation called the dot product, and it is wonderfully straightforward. Step 1, you just multiply the corresponding elements together. Step 2, you add those results together. Multiply, then add. Simple, right? But why does this matter so much? Because this specific mathematical action perfectly models what a single, individual neuron does in an AI. A neuron takes in data, multiplies it by its learned weights, and adds them all up into one single weighted sum. So, the crucial point here is making sure these pieces actually fit together when we try to multiply them. And for that, we have the absolute golden rule of matrix multiplication shapes. If you want to multiply 2 matrices, the inside numbers of their dimensions absolutely must be equal. If you have a 3 by 2 matrix, you can only multiply it by a matrix that starts with the 2, like a 2 by 4. And, the really cool part, the resulting matrix takes the shape of the outside numbers, so a 3 by 2 multiplied by 2 by 4 gives you a brand-new 3 by 4 matrix. Matching these shapes is absolutely essential. I mean, if your shapes don't align, your neural network literally crashes before it even starts. All right, section 4, assembling the neural network. Time to put it all together. Let's actually use y equals wx plus b to predict a student's final marks based on 3 features. Step 1, our input x. We have a student who studies 2 hours, sleeps 3 hours, and had previous marks of 80. Step 2, we apply our weights, the w, letting the network decide how important each feature is. Let's say the network assigns a weight of 0.4 to study, 0.3 to sleep, and 0.1 to pass marks. Now we do our dot product, multiply and add. 2 times 0.4 is 0.8. 3 times 0.3 is 0.9. 80 times 0.1 is 8.0. Add those up and we get 9.7. Step 3,
We bring in our scalar bias, b. Let's say it's a positive 5. So, 9.7 plus 5. Step 4, the result. Our predicted mark, y, is 14.7. Look at that. We just performed a simple linear regression, which is exactly how a single neuron processes data. But wait, we don't want to just predict one student's score, do we? No, we want scale. When y equals wx plus b is applied not just to a single vector, but to a massive matrix of many students at once, the exact same mathematical rules apply. It just calculates multiple predictions simultaneously. And this scale is exactly what happens mathematically inside hundreds and thousands of neurons in an artificial intelligence model. This right here is the computational bridge from simple linear algebra straight into deep machine learning. And that brings us to our final part, Section 5, the big picture. As you dive deeper, you will definitely encounter the term transpose. Now, I know it sounds incredibly technical, but honestly, it's really just a handy formatting trick. Taking a transpose simply means converting rows into columns and columns into rows. Remember our strict shape rule for matrix multiplication? Well, sometimes your data matrix doesn't perfectly fit the weight matrix. Taking the transpose allows you to quickly change the orientation of the data so that your matrix operations and those shape rules line up perfectly. Easy fix. Another intimidating topic for beginners is eigenvectors and eigenvalues. Please, do not let the complex math scare you away today. You just need the conceptual intuition here. When a matrix transforms data, it usually changes the data's direction. But eigenvectors are these special directions that remain perfectly stable. They stay in the exact same direction after a transformation. And eigenvalues, they just tell us how much that special vector was stretched or compressed. You really don't need to calculate them by hand. Just know they are powerful concepts used in advanced machine learning methods, things like dimensionality reduction and computer vision, to find the most important patterns in massive data sets. Now, what's really interesting about this slide is just looking at how far we've come. A scalar is just one number used as our bias. A vector is a list of numbers giving us our input features. A matrix gives us our rows and columns holding our dataset and our learned weights. The dot product is just multiply and add, perfectly replicating a neuron calculating a weighted sum. And the grand finale, y equals wx plus b, takes those weighted inputs, adds the bias, and fires the neuron to make a prediction. We cracked the code. I will say it one more time. A neural network is not magic. At its core, it is just a whole lot of matrix multiplications, dot products, and additions. You are now armed with the mathematical language of linear algebra, and you have officially conquered the master equation of AI. The next natural step on your journey is probability and statistics, exploring things like variance, distributions, and Bayes' theorem. So taking absolutely everything you've mastered today, are you ready to build the statistical foundation behind machine learning? Thank you so much for exploring with me, and I cannot wait to see you dive into the next step of your journey. Welcome to The Explainer. So today, we are looking at something that is literally foundational to modern technology, and that's NumPy. Now, I know it's easy to look at this as, just another coding library you have to memorize. But if we really dig into the source material, we discover what it truly is. It's the absolute mathematical engine behind artificial intelligence and machine learning. Basically, if you want to understand how AI thinks, you absolutely have to understand the math. And NumPy is exactly how that math gets done. Okay, let's dive into this. Here is our roadmap for today. We're going to cover the engine of AI, building blocks like arrays, some NumPy magic, the math of machine learning, and finally, we'll actually build an AI model. All right, Section 1, the engine of AI. To really appreciate this, we first have to ask, why not just use standard Python, right? Well, the truth is, normal Python really struggles under the massive mathematical weight of modern AI. Imagine you've got a data set of student marks. If you want to add 5 bonus marks to everyone, a normal Python list forces you to write a for loop. It goes one by one, basically moving like a turtle. But with a NumPy array, you literally just write marks plus 5. That's it. It does direct, lightning-fast math on the entire data set instantly. And that right there is exactly why it sits beneath pretty much all major machine learning frameworks. Moving right along, Section 2, building blocks, arrays. So, since standard lists are out, we need arrays. Getting comfortable reading these array structures is a super vital skill, mostly because, honestly, shape errors are the absolute bane of every machine learning engineer's existence. Think of it like this.
A basic list of numbers is a one-dimensional array, so it has a 1D shape. But if we start tracking student marks across multiple subjects, well, now we get a two-dimensional grid, or matrix, like a 2x2 shape tracking 2 rows and 2 columns. The big takeaway here? Always ask yourself, what is the shape of my array? Okay, once your data is actually in an array, you've got to be able to access it. And here, you just have to remember
ನಮಸ್ಕಾರ.
one golden
5
rule.
ಅಂಕಿಯ
Python
ಸಂಖ್ಯೆಗಳ
starts counting
ರೋಚಕ
from
ಜಗತ್ತಿಗೆ
0.
ಸ್ವಾಗತ.
So position number
ಇಂದಿನ
1
ಈ
is actually
ವಿಶ್ಲೇಷಣೆಯಲ್ಲಿ
0.
ಸಂಖ್ಯೆಗಳು
If
ಹೇಗೆ
we want a specific
ರೂಪುಗೊಳ್ತವೆ
student's
ಅನ್ನೋದನ್ನ ಒಂದು
math grade
ಆಟದ
pulled out
ಹಾಗೆ
of a 2D
ಹಂತ
grid,
ಹಂತವಾಗಿ
just notice
ಬಿಡಿಸಿ
how
ನೋಡೋಣ ಬನ್ನಿ.
marks
ಇದು
bracket
ಬರೀ
0,
ಸಂಖ್ಯೆಗಳಲ್ಲ,
1
ಗಣಿತದ
pulls the
ಒಂದು
data right
ಅದ್ಭುತ
from the
ಪಜಲ್
first
ಇದ್ದ ಹಾಗೆ.
row, which is
ಆಮೇಲೆ
student 0, and the second
ಸಂಖ್ಯೆಗಳನ್ನ
column, which
ಓದುವುದು,
is subject
ಅವುಗಳ
1.
ಸ್ಥಾನ ಬೆಲೆ,
We can
ದೊಡ್ಡ
also use
ಮತ್ತು
something
ಚಿಕ್ಕ
called
ಸಂಖ್ಯೆಗಳ
slicing
ರಚನೆ
to grab entire
ನದತ್ತ
chunks of an
ಹೆಜ್ಜೆ
array.
ಹಾಕೋಣ.
Like if we wanted to get only the first 3
ಊಹಿಸಿಕೊಳ್ಳಿ,
students
ನಮ್ಮ
all at
ಬಳಿ
once.
9,999
Section 3.
ಅಗರಬತ್ತಿಗಳಿವೆ.
NumPy magic
ಅದಕ್ಕೆ ಕೇವಲ
broadcasting.
ಒಂದೇ ಒಂದು ಅಗರಬತ್ತಿಯನ್ನ
So this is
ಸೇರಿಸಿದ್ರೆ
where we
ಏನಾಗುತ್ತೆ ಗೊತ್ತಾ?
transition into the
ಇಡೀ
features that make
ಲೆಕ್ಕವೇ
NumPy feel so
ಬದಲಾಗಿಬಿಡುತ್ತೆ.
incredibly
ಸಂಖ್ಯೆಗಳನ್ನ
powerful when you're
ಓದನೆಗೆ
handling massive
9ಕ್ಕೆ
data
1
sets.
ಸೇರಿಸಿದರೆ
The
10
crucial
ಆಗುತ್ತೆ.
point here is something
ಹಾಗೂ
called
ಬಿಡಿ
broadcasting.
ಸ್ಥಾನದ ಮಣಿಗಳು
This is where you
ವಿಸ್ತೃತ
automatically
ರೂಪದಲ್ಲಿ
apply
ಬರೆದಿರುವ
an operation
ನಿಖರವಾದ
across an entire
ಮೌಲ್ಯಗಳನ್ನೇ
array
ನಮ್ಮ
without
ಕಣ್ಣು ಮುಂದೆ
writing
ಇಡುತ್ತವೆ.
explicit loops. Like
ಸಂಖ್ಯೆಗಳ
say you want to
ಒಳಗಿನ
convert an
ಮೌಲ್ಯ
array of millions of temperatures from Celsius to Fahrenheit.
ಸಂಖ್ಯೆಗಳು
You just write the
ಚಲನೆಯಲ್ಲಿದ್ದಾಗ
formula once, and
ಹೇಗಿರುತ್ತೆ
NumPy effortlessly
ಈ
broadcasts it
ಅಳಿಲು
across
ಮತ್ತು
every
ಕಪ್ಪೆಯ
single temperature
ಓಟವನ್ನ ಒಮ್ಮೆ
instantly.
ನೋಡಿ.
It's clean, it's
ವೇಗ
elegant,
ಮತ್ತು
and it
ಅನುಕ್ರಮಕ್ಕೆ
completely saves you from
ಇದೊಂದು
writing endless
ಅದ್ಭುತ
for
ಉದಾಹರಣೆ.
loops. And that
ಕಪ್ಪೆ
naturally builds
ಇವೆಲ್ಲವೂ
right into
ಇದೇ ತರ್ಕದ
vectorization.
ಮೇಲೆ ನಿಂತಿವೆ.
Without this,
ಇದು
you're
ನಮ್ಮ
relying on a
ಲೆಕ್ಕಾಚಾರದ
standard
ದಾರಿದೀಪ.
Python loop, just dragging
ಹಾಗಾದ್ರೆ
along step by
5
step.
ಅಂಕಿಯ
But with
ಮೂಲಭೂತ
NumPy
ಅಂಶಗಳನ್ನ
vectorization,
ಕರಗತ ಮಾಡಿಕೊಂಡ
it's a direct
ನಂತರ
calculation
ಆ
happening on the
ನಿಯಮಗಳನ್ನು ಬಳಸಿ
entire array
ಈ
at once.
ಅಂತಿಮ ಸಂಕಲನದ
Operating on
ಒಗಟನ್ನ
a whole
ಹೇಗೆ
block of data
ಬಿಡಿಸಬಹುದು?
instead of looping
ಯೋಚಿಸಿ.
through it piece by piece,
ಒಂದು ಹಳ್ಳಿಯ
that is
ಜನಸಂಖ್ಯೆ
literally the rocket fuel that makes AI
3,399
data
ಮತ್ತು
processing so
ಇನ್ನೊಂದು ಹಳ್ಳಿಯ
incredibly
ಜನಸಂಖ್ಯೆ
fast.
4,890 ಸಂಖ್ಯೆಗಳ
section
ಜೊತೆಗಿನ
4,
ಈ ಕುತೂಹಲದ
the math
ಪಯಣ
of
ಸದಾ
machine
ಹೀಗೆ
learning.
ಮುಂದುವರಿಯಲಿ.
Now that our
ನಮಸ್ಕಾರ.
data is nicely packed into arrays, let's look at the actual statistics that allow AI to learn. There are a few core functions you are going to use constantly. Sum gives us the total. Mean is the average, which is absolutely crucial for calculating how wrong or error-prone an AI model currently is. And then there's STD, the standard deviation, which reveals the spread of your values. Understanding how spread out those scores are is exactly how you normalize data before feeding it into an algorithm. Now, this next one is really fascinating. It's called argmax. Basically, this function tells you the index position of the largest value in a sample array. So let's say we have an array of marks, and the largest mark is a 95, and it's sitting at position 3. Argmax will output exactly that, 3. Now you might be wondering, why is this so vital? Because finding the position of the highest value is exactly how AI classifiers make their final predictions. Imagine a model trying to predict if an image is a dog, a cat, or a bird. It outputs probabilities for each one, right? Argmax just swoops in, finds the position of the highest probability, and boom, that is your model's final prediction. Next up is the dot product. This means multiplying corresponding values in 2 vectors and then adding those results together. So array A is 1 and 2 times array B's 3 and 4 gets us 11. Now, I know it kind of sounds like a simple math trick, but this specific calculation is fundamentally how a neural network processes information. Now, what's really interesting here is seeing this dot product in action inside a simple neuron. A neuron takes inputs, multiplies them by weights, and adds a bias. And in NumPy, we actually use the @ symbol for matrix multiplication to do this instantly. Inputs, outweights, plus bias. That elegant little formula is the literal heartbeat of all neural network computations. Pretty cool, right? Okay, section 5, building an AI model. All right, this is the big moment. We are putting all these concepts together to build a working linear regression model. We've got an anchor data set here, and our goal is super straightforward. We want to predict a student's final exam score purely based on how many hours they studied. So, 1 hour gets a 35, all the way up to 5 hours getting a 70. Our job is to find the mathematical relationship hiding in there, modeled as the classic y equals mx plus c. And this brilliantly illustrates the whole process, because building this predictor really just happens in 4 steps. First step, wrap the data in NumPy arrays. Second, calculate the mean for both of those arrays. Third, we use those means to uncover the weight and bias. And finally, step 4, we get to make entirely new predictions. Now, to extract this relationship, we're going to lean really heavily on the NumPy sum and mean functions we just learned. We compare how far our hours and scores deviate from their averages, we multiply them, and then we sum them up to find our weight.
After that, calculating the bias is really just a matter of subtracting that weight from our averages. By executing this super clean matrix math, we're able to fully expose the exact statistical trend that was just hiding in the data.
Okay, now for the magic moment. We have our weight, we have our bias. What if a student studies for, say, 6 hours? Now, that wasn't in our original training data, right? But by multiplying 6 by our calculated weight and adding the bias, our NumPy setup actually successfully generates a brand new, highly accurate estimated exam score.
To close the loop on this whole machine learning process, we have to know how good our model actually is. So we calculate the mean squared error, or MSE. Basically, we take our predictions, subtract the actual real-world scores, square the difference, and then use NumPy's mean to average it all out. Simply put, the smaller this MSE number is, the better our model fits the training data, and the smarter it is.
So here is a quick memory sheet for your core toolkit, everything from arrays and indexing to broadcasting, vectorization, and matrix math. But honestly, the real takeaway today isn't just rote memorization. It's a complete mindset shift. Because in machine learning, all data, whether it's audio, text, or video, is really just arrays and matrices under the hood. And NumPy is what gives us the engine to manipulate all of it. I highly encourage you to take on these practice tasks from the source material. Try to build your own array of student marks. Find the highest mark using max, and then find its position using argmax. Practice adding those bonus marks using broadcasting, without writing a single loop. You can even try writing that simple linear regression model we just discussed using only NumPy. Hands-on application is absolutely the best way to master this stuff.
And finally, I'm going to leave you with this thought to ponder. Today, we use some really simple arrays, right? Just a few numbers for study hours and test scores. And from that, we built a model that can actually predict the future based on the past. So, what does this all mean? Well, think about what happens when you scale these exact same matrix math principles, not just to 5 students, but to billions of parameters calculating across entire clusters of advanced processors. That right there is the leap from our simple lab today to the massive neural networks driving the world's most advanced AI. Thanks so much for joining me on The Explainer today, and keep exploring the data.
Okay, so you know those incredibly sleek, sophisticated machine learning algorithms everyone's always talking about. Have you ever wondered how raw, chaotic, real-world information magically turns into those predictive models? Well, the truth is, it doesn't happen by magic at all. There's this absolutely essential, yet surprisingly overlooked, bridge between messy datasets and artificial intelligence. Welcome to This Explainer, where we are taking a journey straight into how we manipulate tabular data to make all that AI magic actually happen.
But think about it for a second. What actually happens if you just dump messy, missing, incomplete data straight into an AI? It's a total disaster. I mean, artificial intelligence and machine learning models get all the glory, sure, but they completely fail without meticulously structured data. Garbage in equals garbage out, right? And that is exactly why we need the Python library known as Pandas. It is essentially the gatekeeper that makes machine learning possible in the first place.
Okay, let's dive right into this. Here is our pipeline for today's explainer. Number 1, entering the Pandas library. 2, the anatomy of a data frame. 3, taming messy real-world data. 4, grouping and merging datasets. And finally, number 5, preparing data for ML.
Starting with Section 1, enter the Pandas library, the ultimate ML prerequisite.
So you can really think of Pandas as the ultimate cleanup crew for your datasets. It's this incredibly powerful Python library specifically built to load, view, clean, and combine information. Honestly, whether you download a dataset from Kaggle, some university research project, or a massive corporate database, Pandas is your mandatory first stop. You simply do not touch a machine learning algorithm until Pandas has fully done its job.
Moving along to Section 2, Anatomy of a Data Frame, the structure of data.
All right, if you want to manipulate tabular data on Python, you absolutely have to understand the data frame because the whole concept relies entirely on it. A data frame is a two-dimensional, table-like data structure. It's got row indexes running down the left side and column features across the top. If you've ever used spreadsheet software, a data frame is basically just an Excel sheet living directly inside your Python code. Grasping this is totally crucial for preparing machine learning data.
And let's brilliantly illustrate this with a mock house price dataset. Think about the structure here. Every single row represents just one single entity, in this case, one specific house. The columns, on the other hand, things like area, bedrooms, and age,
Those act as the specific traits or features of that house. These features are the exact variables we might eventually want an AI to analyze and try to predict.
Okay, so you just got a brand new, unfamiliar dataset. What's the very first thing you do? You need its vital stats, immediately. You just run the command df.info. Boom. In literally 1 second, it reveals the total number of rows, every single column name, exactly how many missing values exist, and the specific data types for each and every column. It is hands down the absolute first command you must run to figure out what you're even dealing with.
From there, you're going to want to explore a bit more. Because let's be real, if you have a data set with 100,000 rows, you definitely do not want to print the whole thing out and crash your screen. Instead, use df.head to peek at just the first 5 rows, or df.tail for the last few. df.shape gives you the total two-dimensional size, and df.describe instantly calculates this really handy statistical summary of all your numerical columns. It is by far the smartest way to peek into massive data sets safely.
Which brings us to Section 3, Taming Messy Real-World Data, Handling Missing Values.
Now take a look at these 3 letters, N-A-N. NaN stands for not available. And the reality is, real-world data sets are pretty much never perfect. Sensors fail, humans forget to fill out forms, data gets corrupted. It happens all the time. This leaves us with data sets completely riddled with these dreaded NaN blanks. And if an algorithm encounters a NaN, it usually just breaks. So how do we handle them? We use what's called the imputation pipeline. Step 1, we find all the missing values using isNull.sum. Step 2, we have to make it genuinely tough choice. Do we throw away those rows entirely, or do we try to fill them in? And step 3, if we do decide to fill them, we often replace those missing items with the average or the mean of that specific column. This entire process, like replacing missing student test marks with the class average, is called imputation. And let me tell you, deciding exactly how to handle this is a massive pre-processing decision that heavily impacts your final machine learning model.
Now, another huge part of taming this mess is just filtering it down to exactly what you need. Basically saying, give me only the rows that satisfy a very specific condition, like say students with marks over 80 who are also in the computer science department. But you really have to take note of the syntax here. In pandas, filtering with multiple conditions means you have to enclose each condition in parentheses, and you must use the ampersand symbol for element-wise and conditions. Actually, you can't use Python's normal and keyword here at all. It's a small but totally vital syntax rule for data analysis.
Next up, Section 4, Grouping and Merging Datasets. Combining datasets.
So in the real world, you're practically never handed just one perfectly neat file. Your data is usually scattered across totally different tables. Imagine having a student dataset that just lists names and departments, and then a totally separate marks dataset with names and test scores. You obviously can't analyze them separately. The pd.merge command is absolutely essential here. It acts just like a zipper, seamlessly combining those two tables into one unified data frame by matching up a common column, like the student's name or ID.
Once you actually have that unified dataset, you can start uncovering some amazing high-level insights. And this is exactly where the group by command shines. The group by command physically reshapes your data based on categories. In literally a single line of code, we can tell pandas to group by the department and then calculate the mean of everyone's marks. Suddenly, instead of staring at thousands of individual student records, you are looking straight at the average marks for entire departments. It is incredibly powerful stuff.
Which brings us to the grand finale, Section 5, Preparing Data for ML, the final pipeline.
Enter the famous iris dataset. If you've ever dipped your toes into machine learning, you've probably seen this classic beginner challenge. It contains various measurements of iris flowers. The features include things like petal length and petal width, and the goal, or the target, is to use those specific measurements to accurately predict the exact species of the flower.
So what does a complete pandas pipeline actually look like in this scenario? It is rapid-fire data manipulation. We load up the CSV file. We run df.describe to get the statistical layout of all those flower measurements. We filter the data to only look at flowers with, say, large petals. We use GroupBy to check out the average measurements per species, and then we sort those values in descending order so we can easily spot the biggest flowers first. We are literally watching raw measurements get cleaned, explored, and organized right before our eyes.
And the absolute final step, before we hand this all over to the AI, we slice the data frame right in two. We isolate all the predictive features, like the petal length and width, into one block, and we isolate the target, the actual species we're trying to predict, into another. Separating the inputs from the desired output is exactly how we format data so an algorithm can actually learn from it.
So, the crucial point to remember here is this. Pandas prepares the data, ML algorithms learn from the prepared data. That is the exact boundary between data manipulation and artificial intelligence. Pandas does all the heavy lifting, completely setting the stage so the machine learning algorithm can just step up and shine.
Just to really lock this concept in, let's quickly contrast pandas with another massive Python library you probably know, NumPy. While NumPy is explicitly built for raw numerical calculations, vectors, and complex mathematical arrays, Pandas uniquely specializes in tabular dataset manipulation. NumPy uses arrays, Pandas uses data frames with rows and columns. NumPy does the math, Pandas does the data cleaning and the pre-processing. They are essentially two sides of the very same, very powerful Python coin.
And that brings us to one final kind of wild thought to leave you with. We've seen how Pandas lets us drop missing values, impute averages, and explicitly select specific features for our models. But think about the immense technical weight of those decisions. Knowing exactly how heavily we manipulate this tabular data before the AI ever even sees it, where does the real predictive magic actually happen? Is it inside the incredibly complex machine learning algorithm, or is it fundamentally decided right here, during this exact pre-processing phase? I'll leave you to think about that. Thanks for joining me on this explainer.
Hey everyone, and welcome to This Explainer. Today we're going to be exploring exactly how logistic regression predicts categories. We're looking at how mathematical equations can take raw, messy data and make strict, definitive decisions. If you've ever wondered how a computer can look at a random piece of information and confidently toss it into a specific bucket, well, you are definitely in the right place. Let's see how this math actually comes to life. To really ground this in reality, consider this question. How does a machine actually know what is spam? I mean, every single day you open your inbox and by some kind of digital magic, the phishing scams, the unwanted ads, and the emails from that prince who desperately wants to give you millions, they've all been neatly swept away. But it isn't magic, right? It's a mathematical decision happening in a fraction of a second. So let's unpack how that choice actually gets made. Okay, let's dive into this. Here is our roadmap for today. First, from numbers to categories. Second, the probability engine. Third, crossing the decision boundary. Fourth, the confusion matrix. And finally, number 5, measuring model success. Section 1, from numbers to categories, moving beyond predicting numbers. Up until now, you might be used to models predicting continuous numbers on a sliding scale, like guessing the exact price of a house or tomorrow's temperature. But binary classification is different. It means there are only 2 possible classes. These models turn complex, everyday problems into straightforward zeros and ones. For spam detection, it's either not spam or spam. For disease prediction, a patient is healthy or has the disease. A credit card transaction is not fraud or fraud, and a student result is fail or pass. It's a totally black and white framework. But before a machine can choose class 0 or class 1, we run into a slight problem. Machines just don't understand English text. They only speak math. They only understand numbers. So inputs like the text in a regular email must first be converted into numerical features. A really fantastic beginner technique for this is called TF-IDF. Without getting bogged down in the deep math here, TF-IDF basically looks at the importance of specific words in an email and transforms them into a numerical format that our model can actually read and calculate. Section 2, the probability engine. Transforming raw scores. So, despite its name, logistic regression is actually mainly used for classification, not regression, and it works because of this absolute magic ingredient called the sigmoid function. You see, the basic equation calculates a raw numerical score, and that score could be anything, a massive positive number or a huge negative number. But the sigmoid function takes that raw calculated number and just squishes it down into a really neat value precisely between 0 and 1. Because the output is always between 0 and 1, you can interpret it directly as a probability. Seeing this build step by step makes the whole pipeline incredibly clear. Step 1. The logistic regression algorithm calculates a raw numerical score based on the data's features. Step 2, that score passes through the sigmoid function. Step 3, out pops a probability, let's say 85%. And finally, step 4, the model uses that probability to reach a firm categorical decision. It's just a beautifully logical flow from raw data straight to a final choice. Section 3,
crossing the decision boundary, drawing the line. To actually make that final choice, the model needs a threshold. In standard logistic regression, that threshold is exactly 0.5. If the sigmoid function outputs a probability below 0.5, the model predicts class 0, for example, not spam. But if the probability hits 0.5 or higher, it crosses the boundary, and the model predicts class 1, identifying the email as spam. 0.5 is literally the tipping point. You can kind of think of the model as a strict gatekeeper. By utilizing that 0.5 threshold, basic logistic regression produces what we call a linear decision boundary. It essentially draws a perfectly straight line through the data. Everything on one side of the line is classified as a 0, and everything on the other side is a 1. Now, while not every single classification problem can be solved with a straight line, this linear boundary is the fundamental way logistic regression separates the classes. Section 4. The confusion matrix. Grading the model. Now, what's really interesting is how this simple 2x2 grid elegantly organizes the model's performance. This is called the confusion matrix, and what it does is track every single right and wrong guess by comparing what the model predicted against what the data actually was in reality. If we ran, say, 100 emails through our classifier, every single one of them would land in one of these 4 boxes. Let's quickly break down these acronyms so you know exactly what they mean for your own inbox. TP stands for true positives. These are actual spam emails that the model correctly identified and caught. Awesome. TN stands for true negatives. These are regular, good emails correctly identified as not spam. These two are the correct guesses. But then we have FP, false positives, a regular email incorrectly classified as spam. This is the annoying one, right? Like when an important message from your boss goes straight to the junk folder. And finally, FN, false negatives, when a spam email is incorrectly classified as not spam, landing right there in your main inbox. Section 5. Measuring model success. Turning the matrix into metrics. 2 of the absolute most vital metrics are precision and recall, and it's super crucial to pit them against each other to see the full picture. Precision basically asks, of everything I predicted as spam, how much was actually spam? If precision is high, it means you don't have a lot of false positives annoying you. Recall, on the flip side, asks, of all the actual spam emails out there, how many did I manage to find? If recall is high, it means very few spam emails slip through the cracks as false negatives. Beyond precision and recall, we have a few other key metrics we should talk about. Accuracy is simply the total number of correct predictions divided by the total number of items. Pretty straightforward. The F1 score is a special metric that basically combines precision and recall into a single number. So a high F1 score means your precision and your recall are both reasonably good. Finally, ROC-AUC measures how well the model can distinguish between the 2 classes across various probability thresholds. If you have a really high ROC-AUC, it just means your classifier has a fantastic ability to distinguish spam from non-spam overall. Let's look at a theoretical 100 email test. Let's say our model from the source material had 47 true positives and 45 true negatives. Well, that means 92 out of 100 predictions were completely correct. This shows exactly what accuracy represents. It simply groups all the correct predictions into one massive 92% slice, while the false positives and false negatives make up that remaining 8% slice of errors. So the crucial point is this entirely logical pipeline we just explored. Raw data goes into logistic regression to get a score. That score goes through the sigmoid function to become a probability. That probability crosses a specific threshold to form a decision. Those decisions populate a confusion matrix, which finally generates our metrics. That sequence right there, that is the absolute core of classification. I want to leave you with a provocative thought as we wrap up this explainer. What happens to our precision and recall if we decide to change that classification threshold from 0.5 to 0.7 for something really high stakes, like disease prediction? If we raise the bar to 0.7, the model has to be far more certain before predicting someone actually has a disease. This would definitely increase precision, but it would drop recall, meaning you might actually miss sick patients. It perfectly highlights that this math isn't just numbers on a screen. Moving that threshold changes real-world outcomes. I really hope this explainer has made the inner workings of classification clear and maybe even inspired you to dive into the data yourself. Thank you so much for joining me, and keep exploring.
Welcome back to The Explainer.
Okay, today we're doing something literally game-changing. We are taking the mystery entirely out of machine learning by building your very first real model completely from scratch. If you've ever felt intimidated by ML, or if you're just kind of tired of using high-level libraries without knowing how the engine actually works under the hood, well, get ready. We are going to break it all down step by step so you can see exactly what is happening.
Here is our roadmap for today. We're going to meet your first ML model, learn how to measure your mistakes, see exactly how the model learns, translate all that math into code, and finally wrap it up with the ultimate ML mental model. Let's get right into it.
Section 1. Meet your first ML model, predicting the future with math.
So the core idea here is actually brilliantly simple. Linear regression just learns a relationship between inputs and a continuous numerical output. To make this super concrete, let's look at a highly practical and honestly pretty lucrative question. How do we predict house prices? It's a total classic, and anchoring our brains here is going to make all the abstract math we're about to dive into feel incredibly real.
Okay, let's dive into this. Imagine looking at some data, whereas the house size goes from 1,000 up to 1,800 square feet, the price scales right along with it, say from 30 up to 54 lakhs. Our ultimate goal in machine learning is to find the exact mathematical line that perfectly captures this relationship. Why? So we can instantly predict the price for houses we haven't even seen yet. And the tool we use to find that line? It's y equals wx plus b. This single, elegant little formula is literally the bedrock of simple linear regression when you've got just one feature. Let's break it down really quick. The x is our input, like the size of the house. The y is our predicted output, the price. The w is our weight or slope that tells us how steep our line is. And finally, b is the bias or the intercept, which just dictates exactly where that line starts.
Let's actually see this in action. Say we boot up our model and it spits out a weight of 0.03 and a bias of 0. If we take a 2,000 square foot house and plug that into our x variable, well, 0.03 times 2,000 gives us exactly 60. Boom, a predicted price of 60 lakh rupees. It's so cool because it proves how this totally abstract math directly creates a tangible real-world prediction.
Section 2. Measuring your mistakes. The critic in the machine.
Now here's the catch. Initially, the model is basically flying blind. Those starting weights and biases are just total guesses, so the model desperately needs a reliable way to measure just how wrong its predictions actually are. Think about it. Out in the real world, your predictions are rarely going to match the actual prices perfectly right out of the gate. You might have an actual price of 30, but your model guesses 28. An actual of 40, but a prediction of 43. We're going to be off by a little bit almost every time. This mismatch is exactly why we need error calculation. We have got to quantify these mistakes if we ever want to fix them.
Enter MSE, or mean squared error. Now, I know the formula might look a bit intimidating with that big summation symbol, but conceptually, it is super straightforward. We're literally just taking our actual y, subtracting our predicted y, which we call y hat, squaring that difference, and then just finding the average across all our data points. You might be wondering, why do we square the errors? Well, if we didn't, a positive mistake and a negative mistake would just cancel each other out. The model would sit there thinking it's perfect when it's actually completely wrong. So ultimately, a lower MSE means we have way better predictions.
But MSE isn't the only critic in town. We also have MAE, or mean absolute error. While MSE squares the errors, which by the way, heavily penalizes really huge mistakes and makes it super sensitive to wild outliers, MAE takes a simpler approach. It just takes the absolute value of the error. This makes MAE incredibly easy to interpret in the real world. Seriously, this is the metric you want to use when you actually have to explain your model's accuracy to your boss in plain English. If your MAE is 4 lakh on your housing dataset, it just simply means your model is off by 4 lakh rupees on average. Easy, right?
Now, what's really interesting here is a crucial warning about a metric you're going to hear about all the time, R-squared. R-squared tells us how well our model explains the variation in the target data. If you get an R-squared of 0.90, please, whatever you do, do not fall into the trap of thinking your model is 90% accurate. R-squared measures explained variation, absolutely not classification accuracy. It's a subtle distinction, but a massive one that trips up a ton of beginners.
Section 3. How the model learns. Giving the model a motor.
So, we are finally shifting from static equations to dynamic learning. We're essentially giving our model a motor so we can drive itself forward. And that motor is a brilliant concept called gradient descent. Think of it as a repetitive, sequential cycle. Step 1. The model predicts a value using our trusty y equals wx plus b. Step 2. It calculates the loss using something like the MSE we just talked about. Step 3. It calculates the gradients. These are basically partial derivatives that tell us the exact direction and magnitude of our error. And step 4, it updates the weight and bias to make a slightly better guess next time. By continually calculating these gradients, the model incrementally tweaks its parameters and relentlessly drives down that loss.
Section 4. From Math to Code. Building the Machine.
Okay, so how do we take all these theoretical math concepts and actually turn them into running code on your laptop? Well, let's see how this builds when things get a little more complex in the real world. Because real-world house prices depend on way more than just square footage, right? They depend on the number of bedrooms, bathrooms, the location, you name it. This brings us to multiple linear regression. Adding multiple features simply expands our original equation. We just bolt on a new weight and a new x input for every single new feature we add, while keeping the exact same foundational mathematical logic. When you actually go to write this in code, you basically have two main paths, NumPy or scikit-learn. Implementing the algorithm yourself in NumPy with manual gradients definitely means you have to write more code. But honestly, it is absolutely essential for truly learning the underlying math. Once you totally get it, then you can graduate to scikit-learn. Scikit-learn provides these awesome ready-made algorithms that handle all the optimization efficiently under the hood. In fact, scikit-learn's linear regression function actually uses direct numerical linear algebra instead of manual gradient descent. But writing it from scratch first in NumPy, that is what makes you a true practitioner rather than just a tourist.
And hey, just a really quick reminder on your workflow here. As you implement this in code, a proper machine learning setup always requires separating your data. You have to train your model on one subset of data and then test it on another completely unseen subset. Evaluating your model on unseen data is literally the only way to ensure it's actually learning the underlying patterns and not just memorizing the training examples like a student cramming for a test.
Section 5. The ML Mental Model. The core loop of machine learning.
Let's bring all these concepts together for the ultimate takeaway. This is where we fully connect that raw calculus directly to a functioning machine learning pipeline. So the crucial point is this specific chain of events, and I highly encourage you to burn this sequence into your memory. You take your features, you make a prediction, you calculate the loss, you find the gradient, and you create updated weights. This loop is the most important concept in this entire explainer. It is literally the heartbeat of how a machine learns.
And as your model rapidly fires through this loop, remember your three distinct critics keeping it in check. MAE tells you your average offset in plain terms, MSE highlights your squared errors, heavily punishing those big mistakes, and R squared tells you how well your model is actually explaining the variation in the target data. You now have the exact tools you need to judge precisely how well your model is learning.
So you now know exactly how to build a linear regression model from scratch. You understand the math, you know the loop, the code, and the metrics. But here is a provocative thought to leave you with before we wrap up today. What happens when the relationship between your features and your target isn't a perfect straight line? What if the data curves or clusters or does something entirely unpredictable? Well, that is where machine learning gets truly wild, and we are definitely going to have to explore that next time. Thanks so much for joining me on this explainer. Keep learning, keep building, and I'll catch you on the next one.
So how exactly does a neural network make a prediction? Right? It's kind of the ultimate question. We hear about this AI black box literally all the time in the news and the research everywhere. But what is actually going on inside that box when it gives you an answer?
Well, welcome to the explainer. Today we're going to completely demystify that black box together, focusing entirely on how neural networks make predictions. Now, we all know it's math, it's not magic, but honestly, visualizing it really helps. Think of a neural network like a highly efficient factory assembly line. It takes raw materials in, processes them through all these various machines, checks the quality of the final product, and then, and this is absolutely crucial, it actually recalibrates its own machines to do a better job next time. Okay, let's dive right in. To set up our mental model from the very start, there are three main steps on this assembly line. First, forward propagation. That's simply the factory making its prediction. Second, loss. That's the quality control step, measuring the error or exactly how wrong the prediction was. And third, backpropagation, which is the process of figuring out how to correct the weights inside the machinery so it doesn't make that exact same mistake twice.
So here's our roadmap. Number 1, the machinery. Number 2, the assembly. And number 3, prediction and calibration.
Kicking things off is Section 1, the machinery and its basic components.
The absolute fundamental machine on our assembly line is the neuron. A neuron is really just a unit that receives several inputs and then crunches them through a basic mathematical equation. Z is equal to WX plus B. It calculates a weighted sum of the inputs it receives, and then it applies what's called an activation function to that final sum. Now don't worry about the activation function just yet. We're going to get to that. For now, just know that this single unit is where the core math happens.
All right, let's break down the variables in that equation. What is that W? Well, W stands for weights. Weights are values that determine exactly how important each individual input is to the final decision. Imagine a neuron receiving two inputs. If the second input has a much larger weight than the first, it's going to have a far greater influence on the neuron's calculation. And you know, the entire point of training a neural network is that over time, the network learns the perfect, appropriate weights for every single connection.
Next up in our equation, we have B, which stands for bias. Bias is the standalone value that gives the neuron some much-needed additional flexibility. It essentially allows the neuron to shift its overall results up or down. Because think about it. If we just multiplied our inputs by our weights without adding a bias, our model would be incredibly restricted. It would always be tethered to 0 whenever the inputs are 0. So bias gives the network the mathematical freedom to adjust its baseline.
Weight and bias, they work together in total harmony. If you want to lock this distinction into your memory, weight controls the influence of the input, deciding how loud a specific incoming signal is. But bias shifts the overall result, deciding the baseline volume for the whole neuron.
Moving right along to Section 2, the assembly, looking at activation and hidden layers. So here's the crucial point. A network absolutely cannot just be a series of simple multiplications and additions. If it were, it could only ever draw straight lines to solve problems, and the real world isn't straight lines, right? To understand complex real-world patterns, we need nonlinearity, and that is exactly what activation functions do. They're applied directly to that weighted sum we just talked about, giving the network the ability to curve, bend, and introduce nonlinear logic into how it understands the data.
Let's look at the three main activation functions you really need to know, and exactly when you'd use them. First up is sigmoid. This one is used for binary classification because it mathematically squashes the output into a neat little probability between exactly 0 and 1. Think of your classic yes or no scenarios. Next is RealU, which stands for rectified linear unit. Its main gig is deep inside the hidden layers of the network, outputting anything from 0 to infinity. Basically, if the input happens to be negative, it just outputs 0. Fun fact, RealU is incredibly fast to compute, which is secretly a huge reason why modern deep learning was able to scale up so massively. Finally, we have softmax. This is your go-to for multi-class classification. If you have several possible outcomes, softmax converts the raw scores into a list of probabilities that all perfectly sum up to 1. Whichever outcome has the largest probability takes the win.
Now, when we build an actual architecture, we take all these neurons and arrange them into columns called hidden layers. A network can contain just one, or it could have dozens of these hidden layers. And as we just saw, the neurons inside these layers very often use the ReLU activation function. The data flows sequentially here. The complete output of one layer of neurons literally becomes the fresh input for the very next layer, passing that information deeper and deeper into the network.
And that brings us to Section 3, prediction and calibration, where we finally run the machine.
All right, so this brings us right back to forward propagation. As we established earlier, this simply means passing inputs through the network from start to finish to produce a prediction. Let's make this tangible. Say we feed our network input data about a student, like exactly how many hours they studied. The network takes that, passes it through all those weighted connections, adds the biases, fires the activation functions layer by layer by layer,
and boom, it spits out a final result, 75%. Because our question was, will the student pass or fail, a simple binary question, the final neuron probably used a sigmoid activation function to give us this clean 75% probability that the student will pass. That entire journey from the raw input data to this final percentage, that, my friends, is forward propagation.
But wait, what if the student actually ended up failing the test? Yeah, our prediction wasn't perfect. And this is exactly where loss comes into play. The loss function is our factory's quality control manager. It measures exactly how wrong the network's prediction is compared to reality. If the prediction was super close to reality, the loss is a very small number. If the prediction was way off base, the loss is large.
The ultimate goal of the entire training process is simply to minimize this loss. So, we have a loss. We know for sure we made an error. How do we fix the machinery? Enter backpropagation. This right here is where the absolute magic of AI learning actually happens. Backpropagation sends instructions backward through the network. It systematically determines exactly which weights contributed to that specific error and in which direction those weights need to change to avoid making that same mistake next time.
The mathematical engine that actually executes this weight update is called gradient descent. Conceptually, it takes your old weights, looks at the gradient of the loss, which you can sort of think of as the slope of the error, and applies a learning rate to calculate brand new, much better weights. Now don't stress about calculating the complex derivatives manually right now. Just understand the core concept. Gradient descent is the mechanism used during backpropagation to upgrade the old weights into new weights.
Which brings us to the complete training loop. Step 1, input your data. Step 2, forward propagation makes a prediction. Step 3, calculate the loss to see just how wrong that prediction was. Step 4, use backpropagation and gradient descent to actually update the weights. And Step 5, repeat. You do this thousands, sometimes millions of times. And iteration by iteration, the loss drops, the weights get perfectly tuned, and the network genuinely gets smarter.
Look, if you only take away one single thing from this entire explainer, please make it this. A neural network makes a prediction using forward propagation, measures its error using a loss function, and learns by using backpropagation to update its weights. That is the essence of absolutely everything we have discussed today. That is the rhythm of the assembly line.
All right, the theory is officially yours. But, understanding how a network learns from its mistakes is one thing. What are you going to build when you actually get your hands dirty and manually perform these steps tomorrow on day 15? The machinery is waiting for you. Thanks for joining me on this explainer, and I'll see you next time.
Welcome back to the Explainer. I am so thrilled to have you here today. If you've ever stopped and wondered how artificial intelligence actually looks at the world and, understands what it's seeing, you are absolutely in the right place. Today, we're taking a fun, super approachable journey into the mechanics of machine vision. So get ready, because by the end of this explainer, the magic of AI vision is going to make total logical sense to you. So think about this for a second. How does an AI actually recognize a cat? When we look at a photo of a cat, our human brains instantly see fur, whiskers, those little pointy ears. It's totally effortless, right? But an artificial intelligence doesn't have eyes. It doesn't have a biological brain. The illusion is that the AI sees a picture, but the reality is deeply rooted in some incredibly clever math. So how does it bridge that gap? Okay, let's dive into this. Here is our roadmap for today. First, how computers see images. Second, finding patterns with filters. Third, shrinking and refining data. Fourth, making the final prediction. And fifth, we'll wrap up with your CNN practice challenge.
Section 1. How computers see images.
The real star of our show today is the CNN, which stands for Convolutional Neural Network. Now, simply put, this is a specific type of neural network that is specially designed for working with images. It is literally the powerhouse behind modern facial recognition, self-driving cars, medical image analysis, you name it. But before we get into the heavy lifting, just anchor yourself to this one concept. A CNN is just a highly specialized tool built specifically for visual data. So, here's the basic pipeline of how a CNN operates. It's kind of like an assembly line. It starts with the raw image, then it detects small, simple patterns. Next, it combines those small patterns into larger ones, which helps it actually understand the object. And finally, it predicts the class, meaning it confidently says, this is a dog or this is a car. This step-by-step roadmap is how a CNN gradually converts an image into a prediction. But here is the crucial foundational step you've got to remember. A CNN doesn't initially understand cat, like at all. When you feed it a picture, it only sees numbers representing pixels. To a computer, that beautiful photograph of a cat is just a massive grid of numbers, with each number representing the brightness or color of a specific tiny square on the screen. This is one of the most important ideas to grasp today. Everything starts as just math.
Moving on to Section 2. Finding patterns with filters. So to find these patterns in that giant grid of numbers, the CNN uses something called a kernel or a filter. A kernel is really just a small matrix of numbers that moves across the larger image.
I want you to think of a kernel like a tiny magnifying glass, systematically scanning across a document. As it scans, it's looking to detect very specific, simple patterns. Things like vertical edges, horizontal edges, sharp corners, curves, or textures.
Now, what happens after that magnifying glass does its job? Well, when a filter scans an image, it produces something called a feature map. The feature map basically answers a single question. Where in this image did I find the exact pattern I am looking for? And here's the kicker. If we use 32 different filters, we get 32 entirely different feature maps, with each one tracking a totally different visual clue.
Of course, we actually have to tell our little magnifying glass how fast to move. This is a setting called stride. If our stride equals 1, the filter moves just 1 pixel at a time, examining the image very, very carefully. But if our stride equals 2, the filter jumps 2 pixels at a time. And this brilliantly illustrates a key rule. A larger stride produces a smaller output feature map, because we're essentially skipping over data to speed up the whole process.
But as that filter scans and produces feature maps, our image size naturally shrinks. To fix this, we use something called padding. Think of padding like adding a blank, zero-value picture frame around our original data grid. Why do we do this? Well, mainly to preserve the original image size, to allow those important border pixels to participate more in the calculations, and to control the overall size of our feature maps. The most common type is zero padding, where we literally just add zeros around the edge.
All right, Section 3, Shrinking and Refining Data.
Immediately after our convolution step, we apply something called ReLU, which stands for Rectified Linear Unit. Its job is incredibly simple but absolutely vital. It just changes any negative numbers in our data to 0. So why does this matter? We use ReLU to introduce nonlinearity guys. This is the secret sauce. Without it, the network could only ever understand straight linear relationships. By adding ReLU, the CNN gains the power to learn incredibly complicated, real-world patterns.
After ReLU, we need to shrink our map. We do this through a process called pooling, specifically max pooling. Think of max pooling like taking a bright neon highlighter and only keeping the absolute strongest, most important features from our map. If you have a 2x2 window of numbers, max pooling just looks at those 4 numbers, grabs the biggest one, and literally throws the rest away.
Now, you might be wondering, why throw data away? Because the benefits of pooling are massive. First, it drastically reduces computation time. Second, it reduces the memory required. Third, it helps control overfitting, meaning the network doesn't just blindly memorize the exact training image. And finally, it makes the network highly robust and less sensitive to small shifts in the image. If a cat is slightly to the left or right, pooling ensures the network still recognizes it.
And here's the thing. A CNN doesn't just do this process once. It repeats these steps, convolution, ReLU, and pooling, over and over in multiple layers. Layer 1 might just detect simple edges. Layer 2 combines those into textures. Layer 3 forms actual parts, like a nose or an eye. By layer 4, the network is detecting whole objects. Basically, the deeper we go, the more complex the features become.
Section 4. Making the final prediction. So, up to this point, our data has been living in a 3D block of feature maps. But a traditional neural network can't read a 3D block. It needs a single straight line of data. That is exactly what the flattened step does. It simply takes our 3D feature representation and unrolls it into a single one-dimensional vector, teeing it up perfectly for the final stage.
That flattened line of data is then passed into the fully connected layer. You can kind of think of the fully connected layer as the ultimate detective. It looks at all the complex features the earlier layers found, the edges, the textures, the shapes, and it asks the final most important question. Okay, I detected all of these specific features together. Based on my training, what single object do they represent?
So the crucial point is how it gives us that final answer. To predict multiple classes, the network typically uses a softmax layer at the very end. Softmax takes the detective's findings and turns them into confident percentages. It doesn't just say cat. It says, I'm 85% sure this is a cat, 10% sure it's a dog, and 5% sure it's a car. The highest percentage wins, and boom, we have our classification.
And finally, Section 5, your CNN Practice Challenge.
To truly grasp this, let's do a quick recap. Here are the 5 absolute must-remember terms we demystified today. The kernel, or filter, is our magnifying glass searching for patterns. The feature map is the result of that search. Stride is how fast the filter moves. Padding is that blank zero-value frame we add to the border. And pooling is our highlighter, keeping the strongest features to reduce the map size.
So here is your practice challenge.
I want you to literally take a tiny grid of numbers on a piece of paper and manually trace it. Apply a 3x3 kernel, calculate the math, move your stride, create a feature map. Apply really to drop the negatives, do a max pooling to shrink it, flatten it out, and explain the final classifier. Doing this manually means you will truly understand the core mechanics, completely moving past just memorizing the jargon.
Because once you realize that machine vision isn't magic, but rather an incredibly logical sequence of filters and math, a whole new world opens up. If you can trace a single image from raw pixels to a final prediction today, what complex patterns will you teach an AI to see next? Thank you so much for joining me on this explainer. Keep exploring, and I'll catch you next time.
Okay, let's jump right into this explainer. We're going to demystify the core intuition behind the transformer architecture, and don't worry, absolutely no math degree is required here. If you've been following the massive explosion in AI lately, you've definitely felt the impact of transformers. They're the engine running the whole show. But instead of getting bogged down in complex matrices and endless equations, we're going to do something a little different. We are going to look at the basic 3 steps behind this technology so you can really conceptualize how a machine actually learns to read, understand, and generate human language.
Now, take a look at this sentence. The cat sat on the mat because it was tired. When we read that, our brains effortlessly connect the word it to the cat, right? Because we intuitively know cats get tired, whereas inanimate mats, well, they generally don't. But traditional computers struggle massively with this. To a machine, words are just isolated symbols, and they change meaning based entirely on their context. This single, tricky pronoun perfectly captures the historical roadblock in natural language processing. So, to see how modern AI brilliantly solves this context problem, we'll explore the basic 3 steps behind the transformer pipeline. Step 1, text to tokens. Step 2, tokens to embeddings. And Step 3, the attention mechanism. Then we'll zoom out to look at encoders and decoders before wrapping up with a core intuition. Let's get into it.
Step 1, text to tokens, breaking down the language. Since computers can't just read text directly like we do, they need a way to actually digest our written language. And that's exactly where tokenizers come in. The tokenizer literally chops up human sentences into manageable pieces, which we call tokens. It's kind of like breaking down a massive, complex Lego structure into individual, recognizable Lego bricks. Sometimes a token is a whole word, but modern tokenizers are incredibly clever. They'll often split a larger word into smaller subwords. This just ensures the model can handle a huge vocabulary without getting overwhelmed, basically organizing the raw text before converting it all into numbers. Step 2, tokens to embeddings, giving those chopped up pieces a baseline meaning. So what exactly is an embedding? Well, since a neural network can only really crunch numbers, an embedding translates a word or token into a numerical vector representation. You can think of this vector as a rich numerical profile that holds baseline information about that specific token. Basically, it takes a concept like, say, apple, and turns it into a massive list of numbers capturing traits like its fruitiness, its roundness, or its color. This gives the neural network a way to actually measure and compare words mathematically. But here's the massive problem with using just embeddings alone. Take a look at this comparison. Item 1 is bank, as in the site of a river. Item 2 is bank, a place that holds your money. Identical words, completely different meanings. If an AI just relied on static embeddings, it would pull up the exact same numerical vector for both versions of the word bank. It wouldn't know if you were going fishing or cashing a check. This proves, for sure, that a good language model desperately needs to understand the surrounding context of a word to actually function properly.
Step 3, the attention mechanism, weaving that context together.
To figure out what our earlier it meant, we use something called self-attention. Self-attention is a mechanism where tokens in the exact same sentence literally pay attention to each other to determine their contextual relevance. So instead of looking at words in total isolation, self-attention asks, hey, which other words in this sentence should I be focusing on right now? By actively analyzing the relationships between all the words simultaneously, the model starts to weave together a web of meaning. How does it actually pull this off? You can just think of self-attention like a really sophisticated database search using 3 specific elements: a query, a key, and a value. The query is the token asking, what information am I looking for? The key is every other token announcing, here is the information I contain. And the value is the actual payload. What information should I retrieve if there's a match? And this illustrates the flow perfectly in 3 steps. First, the target token, let's say our word it, creates a query. Second,
All the other tokens in the sentence, like cat, sat, and tired, provide their keys. Third, the model compares the query against the keys, finds the best match, and retrieves the values to build a rich context. The token essentially interrogates its neighbors, compares their answers, and pulls the relevant data to construct a vastly improved, context-aware representation of itself. Now, you might be wondering how it decides what the best match actually is. The answer is softmax. Softmax math converts those raw query and key comparisons into relative importance weights, deciding which words matter most. Look, you don't need to memorize any complex equations here. Just know that the math simply assigns higher attention weights to the most relevant tokens. In our first sentence, the mathematical connection linking it to cat receives a super high weight, while the link to Matt gets a much lower weight. The model literally calculates where its attention should be focused. However, there is a catch. One of the biggest advantages of transformers is that they process all these tokens in parallel to save immense amounts of computing time. But because they process everything at once, we run into a major issue where identical words in a different order lose their distinct meaning. Check out these two sentences. Dog bites man and man bites dog. Exact same tokens. If you just throw them all into the system simultaneously, the model might view them as mathematically identical, completely missing the very different real-world implications of those two events. Which brings up a vital architectural hurdle for transformers. If everything is processed at the exact same time, how does the model know where a token occurs? How does the AI avoid confusing who is actually biting whom? The answer is positional encoding. It takes the original token embedding and adds specific position info. It artificially injects order info directly into the numerical tokens, so the model knows exactly where each word sits in the sentence. It effectively stamps a serial number on every single word. Thanks to this clever trick, the model gets all the insane speed of parallel processing without losing the critical sequence of human grammar. Now let's see how this all fits together. Zooming out, encoders and decoders. As you explore AI, you'll definitely hear the phrase multi-head attention. Don't let the technical jargon throw you off. It just means the model runs several of these exact same attention mechanisms at once to look at the same sentence from different perspectives. Imagine a team of detectives at a scene. One asks, who is doing the action? Another asks, where is it happening? A third asks, when is it happening? Multi-head attention lets the AI capture multiple different relationships within a single sentence all at the exact same time. These multi-headed attention mechanisms are then housed inside larger components called encoders and decoders. An encoder's main job is to thoroughly understand the input. Google's BERT is a famous example here. A decoder's main job is to generate brand new output, piece by piece, which is the foundational architecture behind OpenAI's GPT models. The original transformer actually used both an encoder and a decoder together, and knowing that distinction is absolutely key to understanding today's AI landscape. Finally, the core intuition. Why transformers revolutionized AI? To truly grasp the magic here, let's return to our original problem, but we're going to change just one single word. The cat sat on the mat because it was comfortable. We swapped out tired for comfortable. Instantly, the surrounding context shifts. The attention mechanism recalculates its queries and keys, dynamically updating its weights. It mathematically realizes that a mat is way more likely to be comfortable than a cat. So the high attention weight shifts, and the model understands that it now refers to the mat, not the cat. This leads us directly to our final takeaway. A transformer uses attention to dynamically determine which parts of the input are important for understanding each token and building a contextual representation. So if you remember just one thing from this explainer, let it be this. Transformers revolutionized AI by finally giving computers the mathematical power to intuitively grasp the fluid nuance of human context. Which leaves us with a truly fascinating question to ponder as this tech evolves. If mathematical attention is what finally allowed machines to decode our context, what hidden layers of context in our own human language might AI soon discover that we haven't even noticed ourselves? Welcome to This Explainer. Today, we're diving into a genuinely fascinating topic, how large language models actually predict the next tokens. You know, if you've ever interacted with an AI and kind of just assumed it was looking up answers in some giant magical database hidden out there in the cloud, well, prepare to have that illusion beautifully shattered. We're going to look right under the hood to see the literal mechanics driving this whole technology. I really want you to think about this super simple question. How does an AI actually write? Think about it. When you hit enter on a prompt, the text starts streaming across your screen, right?
It's almost like a ghost is typing it out in real time. It completely feels like it's thinking. But what is mechanically happening inside that system to make that text appear, word by word?
So the crucial point is this. An LLM generates text by repeatedly predicting the probability distribution of the next token. I really want you to burn this concept into your mind because this single sentence is the absolute foundation of literally everything we're going to learn today. The AI is not thinking in paragraphs. It's just mathematically guessing the next piece of the puzzle over and over again. Here's our roadmap for this journey. Number 1, the prediction engine. Number 2, tokens and embeddings. Number 3, the generation loop. Number 4, controlling the AI. And finally, number 5, fine-tuning versus RAG. We're going to zoom all the way in and then back out. Okay, let's dive into this. Section 1, the prediction engine, how it works. At a really fundamental level, an LLM, or large language model, is simply a neural network. It's been trained on a massive amount of text so it can learn all the patterns in human language. But here's the secret. It doesn't actually know facts the way you and I do. Nope. It just looks at the text it's seen so far and learns to guess what's most likely to come next. So why does it need such a crazy amount of text to pull this off? Well, human language is incredibly complex. It's filled with nuance, slang, and weird context. To accurately predict what word follows something like peanut butter and, it needs to have seen that exact phrase and millions just like it across countless different contexts during its training. When you get right down to it, it's essentially the world's most sophisticated autocomplete. Section 2, tokens and embeddings. Processing text. Now, let's zoom in a bit on the micromechanics, because to truly understand how an AI predicts things, we have to know what it's actually looking at when it reads. You see, LLMs don't process whole words like humans do. Instead, they process what we call tokens. A token is simply a unit of text. Depending on the specific tokenizer the model uses, a token might be a full word, sure, but it could also just be a tiny piece of a word or even a single punctuation mark. So a word like hamburger might literally be chopped up into ham, burr, and jur. So why does chopping words up into tiny pieces matter to you? Well, practically speaking, tokens completely dictate the limits of the AI. Your token count directly affects things like your context window usage, the sheer computational power needed, the inference cost, and even the maximum length of your prompt and output. So when you're building an app and you hear that a prompt has 2,000 tokens, just remember that doesn't necessarily mean 2,000 words. It's often way less. Right, so computers don't read English, or Spanish, or any human language for that matter. They read math. So these token IDs are converted into multidimensional numerical vectors, which we call embeddings. Basically, we take a text token, find its ID, and turn it into pure mathematics. By doing this, the AI actually maps out relationships between words in this massive mathematical space. Words with similar meanings end up literally closer together in that space. These numerical vectors are what the underlying transformer network actually processes. I mean, take a second to let that sink in. The beautiful, flowing poetry an AI generates is literally just complex math at its core. Section 3, the generation loop, step by step. Okay, we've got our pieces on the board. Now for the really exciting part. This is where the magic happens, and it operates like a relentless, high-speed assembly line. Let's move to and see how this builds. Step 1, tokenization chops up your prompt. Step 2, embeddings turn those tokens into math. Step 3, the transformer layers process those vectors using mechanisms like self-attention, weighing exactly how each token relates to the others. Step 4, the model calculates the probability of the next possible tokens. And finally, step 5, it selects a token. Then, and honestly this is the amazing part, it loops that newly selected token right back into the input and runs the entire 5-step process again, over and over and over, until the model finally hits an output limit. And this brilliantly illustrates that crucial probability step. If the text processed so far, as Paris is the model doesn't just pull the word capital out of some static database entry somewhere. It actively scores the most probable next pieces of the puzzle. It calculates that, hey, there's a 75% chance the next token should be capital, a 15% chance it's city, and a 10% chance it's largest. It maps out this whole distribution of possibilities before picking a winner. It's literally a game of high-stakes, high-speed probability happening in fractions of a second. Section 4, controlling the AI, guiding the model. Let's zoom back out slightly to the director's chair. We know the engine runs on high-speed probability, right? But how do we as humans actively influence it? First, we have to really grasp the concept of the context window.
This is the model's current working space. Think of it kind of like a temporary whiteboard. And it's incredibly important to remember that this is not the model's permanent memory. I seriously cannot stress this enough. If information isn't actively placed onto that whiteboard through your prompt, the model just cannot use it. It doesn't magically remember a document you showed it yesterday unless you provide it again in the current context.
Then there's the temperature setting. If you set a low temperature, the AI becomes much more predictable. It strongly favors those top, high-probability tokens. Basically, it plays it very safe. But if you set a high temperature, you get a ton more variation. Suddenly, lower probability options get a much better chance of being picked. You absolutely must keep in mind, though, tweaking the temperature merely changes the randomness and diversity of the text. It absolutely does not make the model more intelligent, it just makes it more or less adventurous.
Section 5. Fine-tuning versus RAG. Upgrading the AI. All right, let's zoom all the way out now. How do developers actually upgrade this underlying engine to handle massive, specialized real-world tasks? Well, if you want an AI to know about your specific organization's internal documents, you generally have two paths to compare: fine-tuning and RAG. Fine-tuning actually requires additional training to change the model's internal parameters. It's absolutely great for teaching a model a specialized behavior or a specific style. On the right, though, we have RAG, which stands for Retrieval Augmented Generation. Now, RAG doesn't normally change the model's parameters at all. Instead, it acts more like an open book test. It retrieves external, up-to-date information and supplies it right into that temporary whiteboard context window we just talked about. Now, what's really interesting about this slide is how it forms this wonderfully simple mental model. Prompting and RAG simply change the instructions and give the AI fresh information to use. Fine-tuning, on the other hand, actually teaches the model how to behave and permanently changes the model itself. So if you just need the AI to reference your updated university attendance policy, use RAG to hand it the document. But if you need it to perfectly analyze complex legal jargon every single time and in a very specific way, you might want to actually fine-tune it. So the very next time you type a prompt into an AI, I want you to remember what's really happening behind the screen. Your next chat interaction is just a massive machine doing high-speed probability math. It's rapidly chopping your words into tokens, converting them into multidimensional vectors, and running this lightning-fast loop to guess the next piece of the puzzle, just one token at a time. Which leaves us with one final, fascinating question. If this incredibly complex, seemingly intelligent system is ultimately just doing high-speed probability math, at what point does guessing the next word become indistinguishable from actual thinking? Hey everyone, and welcome to This Explainer. I am super thrilled to have you here today. Look, if you've been working your way toward building advanced computer vision pipelines, things like face detection, gaze estimation, or running those heavy convolutional neural networks, you are in exactly the right place. But right off the bat, before we can get to tracking eyes or detecting objects, we really have to shatter our basic understanding of what an image actually is. So let's dive right in and explore the absolute foundation of computer vision, how computer images actually store and represent data. So I want you to think about this for a second. When you look at a photograph of, say, a breathtaking mountain landscape, or even just a picture of your cat on your phone, you instantly see shapes, colors, and meaning. But what does a computer actually see when looking at that exact same image? Well, I can tell you it certainly isn't seeing a fluffy cat. It literally has zero concept of ears, whiskers, or trees. Okay, here is the big secret, and honestly, it perfectly highlights the divide between human and machine perception. To a computer, an image is nothing more than a massive matrix of numbers. That's really it. It's essentially a giant microscopic spreadsheet where every single cell contains a number, and that number represents the intensity or brightness of a specific pixel. If you take a purely grayscale image, it's just one flat two-dimensional grid of these intensity values perfectly organized into rows and columns of pure data. Now, if we zoom all the way down into that matrix, we hit the pixel. The pixel is the smallest individual element of a digital image. It's basically the tiny little data container storing our information. So how do we find one specific pixel in this massive grid? We access it using indexing, specifically *YX. Now, I know this trips a lot of people up, but it actually makes total sense when you remember that images are stored as matrices in computer memory. You are calling the row first, the height or the Y coordinate, followed by the column, the width, or the X coordinate. It's just standard row major order from linear algebra, and you just kind of have to get used to navigating it that way. Now, speaking of things you have to get used to, there is a super quirky but absolutely vital difference in how these pixels are organized depending on which library you're using. In standard representations, like if you're pulling in Matplotlib, PyTorch, TensorFlow, whatever, a color image uses 3 channels ordered as red, green, and blue. Good old RGB. But OpenCV? Well, OpenCV actually reads color images backwards in BGR order, blue, green, red. Why? It actually comes down to legacy hardware reasons. Early camera manufacturers and software developers back in the 1990s used BGR as their standard output, and it just stuck. So always remember to mathematically flip BGR to RGB if you're passing an OpenCV image array to another modern library, or your colors are going to look completely alien. But hey, what if we don't need color at all? That brings us to the number 1. When we convert a color image to grayscale, we mathematically strip away all those complex blue, green, and red data channels. We condense the whole shebang down to just one single, hardworking channel of pure intensity. Suddenly, a bright white pixel is just represented by the number 255, and a pure black pixel is just a 0. It's an incredibly efficient way to store structural data without the heavy memory footprint of multi-channel color.
And honestly, efficiency is the name of the game here. Before our computers can really see and detect objects, we have to simplify all those raw numbers. We got to strip away the noise and condense our dense data matrix to make it actually digestible for the algorithms that are going to process it. Pretty much every step from here on out is just a mathematical transformation of that initial grid of numbers.
To do that effectively, we really need to know which color representation to use. Let's unbox our color tool belt. RGB or BGR gives you 3 channels of data. That's your go-to for general color images. Grayscale gives you 1 channel and is absolutely perfect for intensity and shape processing, where color would just be a computational distraction. But there's a third one you need to know: HSV, which stands for hue, saturation, and value. HSV also uses 3 channels, but instead of mixing red, green, and blue, it separates the base color, the hue, from its intensity and lightness. If you want to computationally identify something that is, say, approximately red, a process we call color segmentation, HSV is a total game changer because it isolates the color data into one easily filterable channel. Okay, once we've picked our color space, often the very next step in simplifying our data is this powerful transformation called thresholding. Thresholding is kind of a magic trick. It takes a grayscale matrix of numbers, ranging from 0 to 255, and converts it into a perfectly crisp, high-contrast binary state. We literally iterate through every pixel and say, look, if your numerical brightness is above a certain value, you become pure white, a 1. If you're below it, you become pure black, a 0. It takes messy, complex, continuous pixel data and turns it into a stark, binary world that our algorithms can easily navigate.
But yeah, there's a catch. If you use global thresholding, you're setting one single hard-coded mathematical rule for the entire image matrix. And hey, that works great for a flat, simple background. But what if your image has tricky shadows, uneven lighting, or a gradient? That's where adaptive thresholding comes in to save the day. Adaptive thresholding is way smarter. It calculates local thresholds based on small, neighboring regions of the matrix, allowing the rules to dynamically vary across the picture. It handles real-world messy lighting like an absolute champion, even if it does cost a bit more processing power to compute all those local averages.
Now, speaking of messy, real images are also full of noise. Just tiny, random mathematical variations in pixel brightness that mean absolutely nothing to us, but will thoroughly confuse your computer's edge detection algorithms. To fix this, we use a Gaussian blur. Think of Gaussian blur like taking a really soft eraser and just gently rubbing it over our data. It mathematically averages out the extreme pixel values by sliding a small weighted matrix, which we call a kernel, over the image. This gently smooths out the data and eliminates those noisy, annoying little speckles before they can cause any problems. And let me tell you, smoothing out that noise is an absolutely mandatory step before we try to find the edges of objects. Finding edges is really where we transition from pure math to actual computer sight. In terms of our data matrix, an edge simply represents a region where the image intensity numbers change significantly and rapidly. You know, like a sharp numerical boundary between a dark object closer to 0 and a light background closer to 255. The most popular method for finding these boundaries is called canny edge detection, and it relies on a classic, highly effective 3-step pipeline. Step 1, convert to grayscale, so we're only dealing with a single channel of intensity data. Step 2, apply that Gaussian blur to mathematically smooth out the random noise so the algorithm doesn't accidentally detect a high-contrast speck of dust as an actual edge. And finally, step 3, run the canny edge detection algorithm. By stripping color and blurring the noise, we set up the math perfectly to trace the true, sharp outlines of the objects in our matrix. Okay, once we have those edges, or honestly any binary image of ones and zeros, we can start physically shaping our data using morphological operations. I love this part. I like to think of it as digital clay sculpting. There are 4 main tools we use to sculpt our binary shapes. And remember, these are just algorithms shifting those ones and zeros around. They are erosion, dilation, opening, and closing. Let's look at the first 2, which are all about shrinking and expanding our data footprint. Erosion tends to shrink white regions. It's like an algorithm is literally nibbling away at the outer boundaries of your white pixels, turning them into zeros. This is incredibly useful for just completely eroding away tiny, stubborn specks of white noise. Dilation, on the other hand, is the exact opposite. It expands the white regions. It puffs them up by turning neighboring black pixels into white pixels, making the edges thicker and stronger. This is absolutely perfect for connecting nearby regions or mathematically closing little gaps in a line. Then we have opening and closing, which are really just clever tag team combinations of the first 2. Opening is an erosion followed by a dilation. It sweeps away small noise by eroding it out of existence, and then dilates the remaining real objects right back to their original numerical size. Closing is a dilation followed by an erosion. It puffs the object up to mathematically bridge and fill in small internal holes, and then shrinks the outer boundary back to normal. These 2 are the perfect algorithmic tools to beautifully polish up our data shapes without distorting the core object. All right, now let's see how this all builds into something incredibly powerful. We've covered color spaces, blurring algorithms, edge detection math, and digital sculpting. It is time for the grand finale. We're going to put all of these individual tools together into the ultimate master workflow for processing image data. If there is literally one classical computer vision pipeline you should memorize from this explainer, it is this one right here. Step 1, grayscale, to simplify the data down to one channel. Step 2, blur, to smooth the noise and average out those mathematical spikes. Step 3, threshold or canny, to isolate the shapes or edges into strict ones and zeros. Step 4, morphology, to computationally clean up the remaining noise and fill the holes. And step 5, find contours, to actually extract the final mathematical boundaries and coordinate lists of the objects from our matrix. Now, obviously, not every single problem needs every single step, but this acts as the perfect foundational mental model for almost any classical vision task you're going to encounter. And listen, this isn't just abstract theory. These matrix manipulations are the exact foundation for real-world applications. An eye analysis pipeline, it might use adaptive thresholding to mathematically isolate the dark pupil matrix values from the lighter sclera. An object detection preprocessing pipeline absolutely relies on grayscale and blur to normalize the data before feeding those numbers into a massive neural network. And detecting the specific shape of a document sitting on a desk, that relies entirely on this exact sequence of canny edge detection and finding contour coordinates. So the next time you look at a digital image, you're going to know exactly what's hiding beneath the surface, a vast numerical matrix just waiting to be manipulated. As we wrap up, I want to leave you with this question to carry into your own projects. What representation should you use? What mathematical preprocessing is needed? And what specific data points do you actually need to extract from your next image? Keep that mindset and you'll be more than ready to conquer complex challenges like face detection next time. Thanks so much for joining me on this explainer, and happy coding! Welcome to the Explainer, where we ditch the magic and build a neural network entirely from scratch using just the math and NumPy. You know, if you've ever felt like artificial intelligence is just a bunch of mysterious spells cast by high-level coding libraries, well, you are in exactly the right place. Today, we're taking the power back. We're going to build a functioning artificial brain, literally piece by piece. All right, let's dive right into this by completely stripping away all the automatic tools. We really want to shatter that whole black box illusion and establish our raw, basic constraints. So for this explainer, we are absolutely forbidding the use of TensorFlow, PyTorch, Keras, or even scikit-learn for the neural network itself. No automatic differentiation whatsoever. Why? Well, because until you build it yourself with pure math and NumPy, it's honestly just a magic trick. By strictly relying on the fundamentals, we force ourselves to understand exactly what is happening inside the machine. So, here is our game plan for today. First, opening the black box. Then, the forward pass, calculating the loss, the backward pass, updating and learning, and finally, running our own experiments. Let's kick things off with step 1, opening the black box and establishing our parameters. Let's start really small by gathering our raw materials. We've got a 3-class classification data set generated right there in NumPy. I know it's tempting to jump straight into complex data sets like MNIST, but we really need a controllable environment first. We're working with exactly 300 samples, and each contains just 2 input features. You can kind of think of them as X and Y coordinates on a simple graph. These samples are going to fall into 3 distinct target classes. What this means is our architecture will flow from 2 inputs straight through a 50-neuron hidden layer that we initialize with small random weights, and finally funnel down to 3 outputs. It's just a really simple, elegant structure that's ready to be trained.
Moving right along to step 2, the forward pass, where we make our very first guesses.
So let's get into our first major step on this assembly line, forward propagation. This is where our network pushes data forward to make its very first prediction. We start by taking our raw input data and multiplying it by the random weights in our hidden layer, and then we add a bias. But here's the thing, raw math isn't enough. We absolutely need nonlinearity. Enter ReLU, the rectified linear unit. We apply ReLU to the hidden layer to filter the signals. It's incredibly simple, really. If a number is negative, ReLU turns it to 0. If it's positive, it just lets it pass through unchanged. It basically acts as a gatekeeper, deciding exactly which signals are strong enough to move forward.
And this brilliantly illustrates what softmax does at the output layer. It acts as our translator. See, the network's raw calculations might spit out messy numbers like 2.5, -1.2, and 0.3. Softmax takes these arbitrary numbers and structures them into highly readable probabilities that essentially build ones, meaning they all sum up perfectly to 1.0. Suddenly, that messy 2.5 becomes a really clean 85% confidence score.
But there's a massive hidden danger here when you're writing this from scratch. Softmax relies on exponential math. If your raw numbers are even a little too high, those exponentials are going to skyrocket, and your computer will literally crash with an overflow error. To prevent our math from just completely exploding, Softmax includes a vital subtraction step for numerical stability. We simply subtract the maximum value from all the raw outputs before we do the exponential math. It keeps everything mathematically safe right before giving us our final predicted class.
Which brings us to step 3, calculating the loss, otherwise known as the reality check.
Okay, so now the network has made a guess. But because it hasn't actually learned anything yet, we need to install our quality control to measure exactly how wrong it is. We use cross-entropy loss to grade the network's initial predictions against the actual correct answers in our dataset. Just think of this as the network's report card. If it predicted Class A with only 10% confidence, but the correct answer actually was Class A, well, the cross-entropy loss function is going to heavily penalize that prediction.
Now, here is a really fascinating fact. Before training even begins, a completely random 3-class network will predictably spit out a starting loss of exactly 1.098. Why is that? Well, because the average confidence for any class is 1/3, and the negative natural log of 1/3 is roughly 1.098. If you build your code and your initial loss isn't hovering right around this exact number, you instantly know your math is broken. And let's be honest, when you're coding from scratch, it almost always is the first time around. It's just a beautiful mathematical sanity check.
All right, on to step 4, the backward pass. It's time to learn from those mistakes.
To fix those errors, we turn on the power with backpropagation. People usually dread the calculus here, but for softmax paired with cross-entropy, the complex math actually simplifies beautifully. To calculate the initial error, you literally just copy your probabilities, subtract exactly 1 from the correct class's probability, and normalize it by dividing by your sample size. That single elegant subtraction of 1 tells us exactly how wrong the output layer was. But obviously, we can't just stop at the output layer. We have to blame the hidden layer too. We pass that error backward using the derivative of ReLU to see exactly how the internal weights contributed to the mess. And here's where the network literally builds ones to learn. Check this out. If the original signal was greater than 0, the derivative is exactly 1, which allows the error to pass right through and fix the weights. If it was less than 0, the derivative is 0, and the error stops dead in its tracks. We are literally tracing the blame backward through the circuitry.
And that brings us to step 5, updating and learning, where we finally apply the fixes.
So we now know exactly who made the mistake, right? The crucial next point is updating the weights so the network performs better next time. This right here, this is the absolute heart of artificial intelligence. By choosing a specific learning rate, which is just a small number dictating our step size, and subtracting these derived gradients from our original weights, the actual, literal learning process finally occurs. The weights are adjusting. The network is adapting. You should really see the beautiful general pattern emerging here. We predict, we trace the error backward, and we update the core variables. Forward, backward, update. Forward, backward, update. You just loop this process thousands of times, and the loss drops from that initial 1.098 down closer and closer to 0. It's not magic anymore, guys. It's literally just iterative calculus.
Which leads us to step 6, running your experiments to test the machine. Look, don't just run the code once and feel good about it. Let's treat this like an actual lab and modify our blueprint to observe what really happens. I highly recommend running these 4 specific experiments. Tweak variables like the learning rate. Make it really big and watch the loss absolutely explode, or make it tiny and watch the network learn painfully slowly. Try changing the number of hidden neurons from 50 down to just 5. Watch how dynamically every single change you make affects the training loss. Because this right here is how you build true intuition, not just write code. Once you have this working flawlessly, you can totally level up by downloading the MNIST dataset yourself and applying this exact same NumPy-only architecture to a much, much harder problem. MNIST is the classic dataset of 70,000 handwritten digits. It's a massive step up from our little 300-sample toy dataset. And remember the golden rule here: no helper libraries. Download the raw files, write the pre-processing logic purely in NumPy, and feed it right into the network you just built. But before you tackle that as you're running experiments with your from-scratch neural network, ask yourself this: what happens when you remove ReLU entirely from the hidden layer? If you just pass the raw linear math straight through, what completely breaks inside the machine? Why is that incredibly simple act of building ones and zeros through an activation function the absolute key to making artificial intelligence work? Think on that as you sit back and watch your code learn. Thanks so much for joining me on this explainer, and happy building.
All right, welcome back, focused learners. So yesterday, you likely tackled the actual nitty-gritty of building a neural network in PyTorch. But today we're taking a massive leap. We are officially moving out of the basic coding phase and stepping right into the control room. It's time to actively diagnose and steer model performance. Look, if you've spent literally any time at all working with machine learning, you've definitely stared at your monitor and asked yourself this exact question: why is my neural network not learning well? What am I supposed to change? Honestly, it's incredibly frustrating to build a model, feed it all your data, and just watch it fail to perform. You kind of feel helpless. But good news, you aren't. You really just need to know which controls to adjust.
Okay, let's dive into this roadmap. First, we'll distinguish between memorizing and actually learning. Then, we'll uncover the 6 training knobs, unmask the twin villains of underfitting and overfitting, learn how to read loss graphs, and finally, apply the whole shebang to the PyTorch loop.
Let's kick things off right now with Section 1, Memorizing versus Actually Learning. Because, spoiler alert, getting a super high score during training does not necessarily mean your network is actually smart.
To really wrap our heads around this, we have to look at the 2 very distinct data sets we use. On one side, you've got your training data. This is what actually updates the model's weights, and it usually makes up about 80% of your total data. But the real magic? That happens on the other side, with the validation data. This is that remaining 20% that the model has absolutely never seen before. It's basically our ultimate truth teller to figure out if the model is genuinely learning or if it's just cheating.
So how do we actually guide the model toward true learning? Well, let's step up to the control panel in Section 2, the 6 training knobs.
Think of these as the physical dials on a massive machine. We've got the learning rate, batch size, epoch, regularization techniques like dropout, and early stopping. Oh, and we also have model capacity, which really just means how large and complex your neural network is. Getting these knobs dialed in perfectly is the absolute secret to a high-performing model. Let's break down what the most critical ones are actually doing under the hood. First up, we have the learning rate. Conceptually, think of this as the step size. It controls exactly how much the model's weights change during training as it kind of walks toward the minimum loss. If you crank this knob too low, the step size is tiny, and your model is going to learn painfully slowly. But if you crank it too high, the model takes these massive leaps. It might literally jump completely over the minimum loss and just fail to converge altogether. So yeah, there's no universally perfect learning rate. Finding that Goldilocks balance is everything.
Next up is batch size. Imagine you have, say, 1,000 images. Instead of trying to process all of them at once, you process them in batches. If your batch size is 32, the model looks at 32 samples before stopping to calculate an update. Now, Turning this knob down to a small batch uses way less memory and gives you more frequent updates, but the training can be pretty noisy. On the flip side, turning the knob up to a large batch provides much more stable gradient estimates and can be super fast on GPUs, but it's going to demand a ton more memory.
Then we have the epoch knob. This one simply controls training duration, meaning one complete pass through your entire dataset. But wait, here's a catch that trips up a lot of people. If you have 1,000 images and a batch size of 20, one epoch does not equal one batch. It actually requires 50 batches to make one epoch. So if you run training for 50 epochs, your network is seeing that complete training dataset 50 separate times.
All right, now that we know our tools, we really need to know what we're fighting against. Moving right into Section 3, Underfitting and Overfitting Explained. These are the twin villains of machine learning.
These two villains operate at total opposite extremes. Underfitting happens when your model is just too simple, or maybe it just hasn't trained long enough. It's exactly like a student who confidently struts into a test having read 0 pages of the textbook. Overfitting, though, is the exact opposite problem. The model becomes obsessively fixated on memorizing the specific training data, but then completely fails on unseen data. That's the student who memorized the practice test word for word, but absolutely panics the second the real exam changes the names in the word problems.
To fight off the overfitting villain, we use a brilliant regularization technique called dropout, and it does exactly what it sounds like. It randomly turns off certain neurons during training. By temporarily ignoring these neurons, you force the network to avoid relying too heavily on any single pathway. It forces the whole model to learn robust, distributed patterns across the entire network. Honestly, it's our primary medication for treating an overfitting model.
So, how do we actually know if our model is infected by one of these villains? Well, we look at the charts. Welcome to Section 4, Reading the Loss Graph. Pay attention, because this is without a doubt the most important graph you'll look at today.
Let's diagnose the symptoms by comparing training loss versus validation loss. If both are going down, excellent, your model is learning beautifully. If both just stay high, that's underfitting. Your model might be too small, or your learning rate is totally off. If both are violently fluctuating, your learning rate is probably too high or your batch size is too small. But if your training loss keeps dropping while your validation loss suddenly starts climbing, warning sirens should be blaring in your head. The model is specializing way too much in the training data and completely losing its grip on reality.
Now, what's really fascinating here is that the best epoch is almost never the last epoch. Look at how the training loss keeps dropping, from 1.20 at epoch 1 all the way down to a tiny 0.12 at epoch 25. The model totally thinks it's a genius. But check out the validation loss. It drops at first, hits a low point of 0.45 at epoch 15, and then slowly creeps right back up. If you blindly grab the model at epoch 25, you are choosing an overfitted, fundamentally worse performing model. Epoch 15, that is the true sweet spot.
And that exact logical deduction leads us beautifully to our next knob, early stopping. Early stopping is precisely what it sounds like. We simply stop training when validation performance stops improving, rather than blindly grinding through all the epochs. We usually control this with a parameter called patience. For instance, a patience of 5 means the training loop will literally wait for 5 epochs to see if the validation loss improves at all. If it doesn't, it automatically pulls the plug before the model starts aggressively memorizing the data.
Let's move to Section 5 and see how this all translates into actual code. Because, understanding the theory is great, but applying it in the PyTorch training and validation loop is where the rubber actually meets the road.
During the training phase, there's a very specific sequence we have to follow. Step 1 is calling model.train. This step is absolutely critical because it enables those training-specific behaviors we talked about. Step 2 allows the gradients to actually calculate updates to the weights. And Step 3 highlights what that model.train call actually achieved. It ensured that our dropout technique is fully active. The random neurons are actively being turned off, forcing the model to learn dynamically. But the validation phase? That is a stark contrast. Here, Step 1 is calling model.eval, which switches the whole model into evaluation mode. Step 2 uses torch.nograd. This explicitly tells PyTorch, hey, do not calculate gradients, because we are just testing right now, not training. That simple step saves massive amounts of memory and compute time. And crucially, Step 3, dropout, is completely disabled. We want the full 100% brain of the neural network functioning when we are testing its real-world performance.
So, it all really boils down to one absolutely crucial question. Is my model actually learning a general pattern, or is it simply memorizing the training data?
Never, ever judge a model purely by its training accuracy. By understanding your 6 training knobs, properly using validation data, and carefully reading your loss graphs, you can ensure your model is truly intelligent and not just a really good copycat. So the very next time you hit run on your code, ask yourself, which one is your model doing?
Welcome to this explainer. Today, we are tackling one of the absolute most fascinating challenges in modern tech, natural language processing, or NLP. We're going to completely demystify the NLP pipeline. We're looking at the exact journey of how we take raw, messy human text and convert it into structured numbers that a machine learning model can actually make sense of. So if you've ever wondered how your computer reads a movie review and just knows exactly how you feel about it, you are in the exact right place.
Okay, let's dive straight into the roadmap. We're going to cover teaching machines to read, chopping and cleaning text, finding the root word, turning words into numbers, understanding semantic meaning, and finally, building a sentiment classifier.
Section 1. Teaching machines to read, bridging the gap between human language and machine math.
So here is the fundamental problem we have to solve today. How do we actually convert raw text into numbers? Humans communicate in this incredibly complex, unstructured, and, let's be honest, highly messy way. But machine learning models, they literally only understand math. They cannot directly read a sentence. So our entire mission in this explainer is going on this evolutionary journey to solve this exact translation problem. We need to build a pipeline that takes a paragraph of text and spits out a neat mathematical representation.
Section 2. Chopping and cleaning text, removing the human fluff.
Right, so before we can do any math whatsoever, we first have to clean up that messy input data. Our very first step in making text manageable is called tokenization. This simply means splitting text into smaller units called tokens. Imagine taking a massive rambling string of text and just chopping it up into bite-sized pieces. You can do word tokenization, where you split it up by every single word, or sentence tokenization, splitting by sentences. We absolutely have to do this because models can't just ingest massive blocks of text all at once. They need these discrete, manageable tokens to even begin their work.
Okay, once we have our tokens, we usually want to declutter, right? So we remove what we call stop words. These are those super common filler words that provide very little useful information to the model. Think of words like a, an, or the. But actually, scratch that. You have to be incredibly careful here. The crucial point is, do not blindly remove stop words. If you're trying to figure out sentiment and you remove a word like not, you completely destroy the actual meaning of the sentence. For example, changing "the movie was not good" into "movie was good" literally flips the reality of that text.
Section 3. Finding the root word, simplifying the vocabulary.
Now, words come in a ton of different forms, and if we don't reduce them down to their base, we're going to confuse our model with a ridiculously massive vocabulary. To fix this, we've got 2 main options. Option 1 is stemming. This is faster, but honestly quite crude. It essentially just chops off prefixes and suffixes. A really popular algorithm for this is the Porter stemmer. But the catch is, it can produce totally fake words. For instance, carrying might just become car. Think of stemming like a fast, but somewhat messy butcher. Option 2 is lemmatization. This is slower, but linguistically way more accurate. It actually tries to produce a valid dictionary-based word. So, under lemmatization, caring correctly becomes care. It's much more like a meticulous linguist.
Section 4. Turning words into numbers, the translation. All right, we have finally reached the climax of our pipeline where our clean text actually becomes mathematical data. Our first, most basic solution for this is the bag of words, or BO. Bag of words converts text into numerical vectors based purely on word occurrence. The model learns exactly which words occur and just counts them. Simple, right? But it has a major flaw. It completely loses the order and the context of the sentence. If you have the sentence, dog bites man, and man bites dog, bag of words might give them the exact same numerical representation just because the raw counts of those words are identical.
So, we solved this counting flaw using a really clever algorithm called TF-IDF, which stands for Term Frequency Inverse Document Frequency. Where bag of words treats all words equally, TF-IDF definitely does not. It mathematically gives a higher weight to words that are frequent in one specific document, but relatively rare across all documents. To put that into perspective, if you're analyzing thousands of movie reviews, the word "the" occurs absolutely everywhere, so it gets a very low importance weight. The word "movie" is common, but a bit more specific, so it gets a medium weight. But a word like "outstanding," that is relatively rare across all the documents, but highly frequent in one specific glowing review.
so TF-IDF gives it a high importance weight to help truly distinguish that text. Section 5. Understanding semantic meaning beyond just counting words.
Here's the thing, though. Merely counting words isn't true understanding, is it? Both bag of words and TF-ID represent words based mainly on their occurrence. That brings us to our next evolutionary step, word embeddings. Embeddings represent words as dense numerical vectors that capture true semantic relationships. This means words with similar meanings actually have similar mathematical vectors. It allows the machine to genuinely understand relationships between concepts. The classic example here is mind-blowing. You take the math vector for king, subtract man, add woman, and the resulting vector mathematically equals queen. We are literally mapping human meaning directly into math.
And there are several popular approaches to creating these embeddings. You'll hear about word-to-vec, glove, and fast text a lot. But the real cutting edge today relies on transformer embeddings, like BERT. Modern NLP models like BERT use what we call contextual embeddings. This means the mathematical representation of a word can actually change in real time depending on the surrounding sentence. The math completely adapts to the context.
Section 6. Building a Sentiment Classifier, your Day 22 project.
Let's see how all of this builds into a practical payoff. To do that, let's just quickly summarize our entire journey. Every technique we discussed solves a very specific problem in the NLP pipeline. Tokenization splits the text. Stop words handles the common fluff. Stemming and lemmatization reduce words to their base. Bag of words counts occurrences, while TF-IDF weights the truly important words. And finally, embeddings represent that deep semantic meaning. So, for your target project, here is the specific, actionable pipeline you're going to use. Step 1, you take in your raw text input, say a movie review. Step 2, you pass that through a TF-IDF vectorization process to convert those words into weighted numbers. Step 3, you feed those numbers directly into a logistic regression model. And Step 4, the model outputs a label predicting whether the sentiment is positive or negative. And honestly, the best part is that implementing this in Python is incredibly accessible. You do not need to jump straight into complex deep learning or massive BERT models today. For your first run, you can just use Python's scikit-learn. You simply import the TIDF vectorizer and logistic regression tools. Create a small text data set, convert your text to those TIDF features, train your classifier model on that data, and then test it with brand new text to get a sentiment prediction. It is a fantastic way to see this math in action.
But as you master this pipeline today, I want to leave you with a bit of a provocative question to ponder for tomorrow. What happens when the exact same word means two completely different things depending on the sentence? Like, think about the word bark on a tree versus a dog's bark. Standard TF-IDF really struggles with this kind of nuance, and that is exactly where deep learning and those advanced contextual embeddings we mentioned will come into play for Day 23. Until then, keep exploring, keep building, and I will see you in the next explainer.
Welcome to the Explainer. I am so thrilled to have you here today because we are crossing a massive threshold in our deep learning journey. If you've been following along with us, you already know the absolute grind of building a neural network completely from scratch. But today, well, today we're leaving all that manual, painstaking math in the rearview mirror. We're going to explore exactly how PyTorch's incredible automation engine takes all that heavy lifting completely off our shoulders.
So let me ask you a question. Are you just completely exhausted by the grueling process of calculating neural network math by hand? I mean, really think about those backpropagation equations for a second. We're talking pages of complex chain rule calculus just to figure out how to update a single solitary weight. And look, it is absolutely crucial to know how that engine works under the hood. But doing it manually every single time you want to build a model? No way. That is a total nightmare for your productivity.
Okay, let's dive into this comparison. Think about yesterday's reality. It meant dealing with messy, manual calculus using basic NumPy math. You actually had to sit there, calculate the exact derivatives for your gradients, and manually write out the code to update your weights. But today's reality? Today is all about PyTorch. All those complex, sprawling equations get transformed into clean, highly optimized one-line functions. PyTorch is essentially this brilliant, automated mathematical factory, and it's designed from the ground up to replace every single manual gradient calculation you used to do. So here is our blueprint for how we're going to build this automation engine today. First, prepping the data engine. Second, building the neural network itself. Third, understanding the 3 key roles. Fourth, the automated training loop. And finally, putting it all together in the complete automation engine. All right, let's get right into step 1,
prepping the data engine. Look, before any factory can actually start producing, it needs raw materials, right? In deep learning, our raw material is obviously our data, and the absolute foundation of this entire PyTorch data engine is the tensor. You can basically think of a tensor